So it's a pleasure and honor for me to introduce Professor Alison Tomlin to give our course. Professor Tomlin is, let's see, graduated from 1987, right? 1990? Okay, anyway, yeah, from University of Leeds, and then actually she came here for postdoc after that, right? Roughly around that. That was the time I joined Princeton. You know that? But we never sort of cross rank. And then she went back to University of Leeds and continued there, and you know, carry on the strong tradition of chemistry at the University of Leeds. And you know, she has been doing you know, all aspects of combustion chemistry and kinetics in terms of alternative fuels, environmental effects, and lately on uncertainty analysis, those hot topics. And she's a fellow of the Combustion Institute, very prestigious. And so basically, you know, carrying the tradition, the outstanding reputation of University of Leeds. When you talk about Leeds, it's Professor Tomlin. And so we're indeed fortunate to have her to give us the course on combustion chemistry. Yes. Okay.
Shall I go? Thank you very much, Ed, for that kind introduction. Well, good afternoon, everybody. It's nice to be back in Princeton. I lived here for a year as a postdoc, as Ed said, in 1993, I think it was. That's nearly 30 years ago now. So just to tell you a bit about myself, I'm kind of a bit of a fake chemist because my first degree is actually in maths and history and philosophy of science. Yeah, so, and then I did my PhD in the School of Chemistry at Leeds. The chemicals that I modeled were A, B, and C. So, but actually, as the years have gone on, I've started to get interested in more and more complex systems. As we'll see, chemical models have got more and more complex. But my background is mathematical, and so for the main part, my work has been really around developing and analyzing chemical models using mathematical techniques. Today, this week I'm going to run through a lot of different aspects of chemical kinetics, going all the way from the molecular scale up to models of devices. I haven't worked in all of these areas. So I've had some help in putting the course together, particularly from Professor Mike Pinning, if you know him. He's from Leeds, and also from Professor Bill Green at MIT. And then bits of input from other people. So a couple of people from my group, Scott Wiseman and Christian Mickelbach, and then help with 1 or 2 slides from Mike Burke, Brandon Rotavera, and Steve Klippenstein. So I'm going to be presenting a lot of work, but I don't actively work in the research in all of these areas. I mean, none of us do, so just bear that in mind. So the background then to the way I want to present things is really as a view to the future. I sort of feel quite strongly about this because I teach climate change science actually at Leeds, and also air pollution science, as well as combustion. And so I quite regularly read the reports from the Intergovernmental Panel on Climate Change. Just had to update my lectures for the new reports that came out at the end of last year and the beginning of this year. So I'm getting a lot of messages around the urgency of the need to act on climate change. And so I feel quite strongly that the energy status quo cannot be maintained, should not be maintained. And obviously there are some strong messages around the fact that we maybe shouldn't be burning stuff, particularly fossil fuels. So if you're a combustion scientist, you're thinking maybe, well, do we have a career in this topic? What can we do? And I hope that you're thinking, what can we do to try and find solutions to climate change? So I guess first question I want to ask is, in a low-carbon future, what role can combustion science and research play, and what role should it? And I strongly believe that we all should be trying at least. It's not so easy, but I think there are some positive messages here. So we basically will be, I think, moving to quite broad-scale electrification of the energy supply system, but that doesn't come without challenges. So I have actually also done some work in wind energy. So I know really that wind and solar are intermittent energy sources. And if we want a stable supply of electricity, even if that's to charge electric cars or it's to power heat pumps, that we need to find some way of storing that energy. Because the demand will be high potentially when we don't have solar, so we might want energy for heat in the winter. And we have, even in the UK, it's pretty windy, but we have long periods where we have calm conditions, and we have to be able to provide a stable power supply. And so there is a real role for various different ways of doing that. One is through energy storage. And we'll be looking at this on day 4 a bit more, I think, but I want to talk about the role of alternative fuels and energy storage. So hydrogen, you'll be aware, is one way of storing electricity through electrolysis, but also e-fuels and potentially ammonia as an energy carrier. Biofuels can be, I suppose, classified as energy storage because you're growing the biomass which is storing carbon from the atmosphere and then potentially using the fuel. And the other approach is to continue to use fossil fuels, but to capture the greenhouse gas emissions through carbon capture and storage. And so there are roles for combustion science in all of these areas. So don't worry, hopefully not going to be completely out of a job or research issues to tackle. And I think an important aspect for me is that as we seek to find solutions to climate change, including combustion technologies, that we should ensure that we're not worsening other environmental objectives. So, for example, emissions to air that affect air quality and human health. So there are questions around, can we burn hydrogen with low NOx? Can we burn biofuels with lower particulates than their fossil fuel counterparts? Can we burn ammonia without ammonia slip to the atmosphere? So there are broader questions around the utilization of alternative fuels. And so it may well be that we have a role for combustion to play in various different energy sectors, so providing heat maybe through combustion of hydrogen, alternative fuels in the heavy-duty trucking industry, for use in shipping, marine engines, in aviation, and in energy power storage and power generation. So I think there are a lot of opening areas. And then even if we are going down a route of large-scale electrification, there are still combustion questions to answer here. So batteries are potential combustors, so we need to understand the safety around heavy use of batteries within storage and within vehicles. If we're going to be storing and transporting hydrogen around and using it in gas turbines, for example, or using it in aviation or in engines, then there are safety considerations which require combustion research. I mean, I don't know if any of you were aware of the tragedy that happened in the UK, the Grenfell fire, where buildings were surrounded in cladding to improve their energy efficiency, so to lower their energy demand, but in fact that cladding was combustible, and that led to the deaths of about 70 to 80 people in that fire. So fire risk from energy efficiency measures is also an important topic. And then we may have future nuclear plant. Hydrogen safety is important there, and safety in gas turbines. So we're not short of combustion topics for future energy scenarios. I don't think that anyone's going to cover necessarily this as a topic this week, but climate change is going to pose additional risks. So wildfires are likely to become more common in warmer climates, drought conditions. And we also have to think about potential for increased air quality risks as temperatures change. So we need to think very hard about emissions from alternative energy strategies. So that's the kind of background of where I'm trying to come from. So as we transition towards the use of lower carbon or other alternative forms of energy provision and utilization, we are likely to need to redesign many of the devices that we're using. So if you take hydrogen as an example, You may be surprised to learn, I was quite surprised to learn, that in the UK, we can tail wind energy on 75% of days of the year because we can't transport the electricity we're producing. So on many days, we're producing more electricity than we can actually utilize. That spare electricity is being wasted, could be used through electrolysis to generate hydrogen. But what would we do with that hydrogen? So we potentially could use it in gas turbines to regenerate power when it's not windy, when we have days of very low wind energy. But it won't be exactly the same gas turbines that we're currently using to burn natural gas. We will have to think about the different combustion properties of hydrogen relative to natural gas, and that's a theme that I'll touch on through the week. And so we will have to redesign some of these devices. I mean, I'm not sure whether or not we will ever see hydrogen in the domestic supply around the world, but it's possible. Again, devices will have to be redesigned to work safely and effectively using hydrogen. Same is true of heavy-duty engines that might operate on biofuels or on ammonia or on power-generated fuels or blends. And so there are questions around whether we can actually design effective devices that will have low air quality impacts based on some of these fuels. So ammonia and metals as energy carriers are two examples there. Okay, so there's a lot of work to do. Probably Thierry is also talking about the same topics from the turbulence perspective in the other lecture theatre, particularly around hydrogen blends. There's also work to do in understanding combustion of batteries. That's not gas phase, so that's too hard for me. I won't be covering it. But that is a future topic, and there are people working on that. And so there are many questions which could be assisted by modelling combustion processes. So using models in the design process to effectively come up with new strategies for gas turbines that can operate on hydrogen or hydrogen ammonia blends or hydrogen methane blends in the short term. All of these models require the coupling of flow and chemical processes. Okay. So I mentioned the word model. So this is the philosophy of science part of me. What do I mean by a model? A model is not reality. I'm sure you all know that. It's an interpretation or an approximation of reality. So it's something that will help us in our design process maybe, or even help us to understand the fundamental science behind the processes that we're trying to model. So my understanding of a model, from my personal perspective, is that it should tell us things we don't know. Otherwise, what's the point of it? If it's only telling us something that we've already measured experimentally, then it's not telling us anything new. It's not worth the effort. And so a model, the purpose of a model really is to extrapolate knowledge. So very often we couple together experiments and models, and coupled together we can use experiments to validate our model, for example. We'll talk more about that later in the week. And then if our model, we're happy with the validation, that we feel it's a robust model, then we can use it to predict things that we haven't measured experimentally. So for example, we might want to use it to design a gas turbine device that we haven't yet built. Okay, so that I would consider to be an extrapolation. So using the model to tell us something we don't know. And it can help us save time and money performing complicated experiments. You know, we can't build tens of different designs of gas turbine and test them all. So a model can really help us there, along with other sustainable processes. So that means that the model has to have certain features. It needs to be general enough to be able to predict across quite wide sets of conditions, temperatures, pressures, equivalence ratios, so that we can, you know, if you think about the conditions in a gas turbine, we might be going all the way from very lean conditions to very rich conditions, broad range of temperatures and pressures. So our model needs to be sufficiently robust to represent all those conditions. And that's not easy to do when we have to validate it over those conditions to ensure that it is robust. So our model might take various different forms, and for a particular process, there might be more than one model that can represent that process at different levels of detail, for example. I mean, that's certainly true in chemistry. Who was in the lectures in here this morning with Professor Matalon? Any of you? Yeah, some of you. So he talked about one-step chemistry versus detailed models. Might be trying to represent the same system, but obviously with differing levels of detail. And there's kind of an expectation that the more fundamental a model is, the closer it becomes to reality. But is that actually true? Professor Matlon talked about this morning. We started out with chemical models into the last century. So Semenov's chain branching and thermal explosion mechanisms would have been the starting point to develop detailed reaction chemistry. But, kineticists have moved on a long way since then. We're now putting together surrogate biofuel mechanisms that might have 10,000 reactions. So does that mean our model is more accurate? Does it mean it's more suitable for the task? Not necessarily, because we have to populate that model with data. Rate constants, thermodynamic data, etc. Okay, so I think we're all going to show this slide from Lumen law. So this is just showing you historically how the size of models have developed. So even the GRI mech is at the bottom of this scale. But if we go up to surrogate biofuels like methyl decanoate, or surrogate fossil fuels, so C16 might be a diesel surrogate, for example, then we're well over 1,000 species. So I guess the question is, well, how reliable is that model? If we're up to 10,000 reactions, then that needs a rate constant for each one of those. So what are the uncertainties involved in that level of detail? And we also need thermodynamic data for maybe 2,000–3,000 species. So I think what I'm saying is it's not a given that just because a model becomes more detailed, that it's necessarily fit for purpose. We have to test that. So we might have many different models for the same chemistry. The top one, called perfect fidelity model, that might be something I inherited from Bill Green, I can't remember. But basically, this is something that we might think we're trying to achieve, but we will never do so. So this is a very large number of species and elementary reactions representing our chemical system with true thermo and rate constants. So, zero error, 100% certainty in those values. And this is a model that we think might predict exactly the true chemistry, but this is something that's not really achievable. And so what we're doing is, with a detailed chemistry model, we're trying to get as close to that as we can. So we're trying to include all of the species and reactions that we think are necessary to model the chemical processes of our system. We're trying to adopt the best known thermo and rate parameters. So that's great, but if I give that to Thierry Poinceau, he's going to go, no, what can I do with that? It's got 10,000 species and I have to model 3D turbulent combustion. So he's not going to like it, and for obvious reasons, because it's very difficult. We don't have the computer resource, basically, to couple that level of detail with reactive flow models. So most often then, if we want to couple with CFD, we're looking to reduce the effort in solving the chemistry. So we're trying to reduce that detailed chemistry model to a reduced model. So I will be doing a whole session on model reduction. It was mentioned this morning, so those of you that were here this morning will have a bit of a background on that. The other type of model are purely empirical models, where we just come up with some kind of functional form for our model and we fit it to some experimental data. And it might be good for our system. You might get a very nice fit between experimental points in our line. The question is that a useful model? Can we extrapolate it to tell us things we don't know? And so empirically fitted models are always more challenging in the sense of extrapolation. So what we want is a model that has quite good fidelity. It's not going to be perfect, but we want good fidelity. But then we might have to reduce it to be able to link it with CFD. So you'll find for particular systems that there'll often be multiple models out there. If you just take natural gas, must be at least 20 chemical mechanisms for methane combustion over the years. And they'll have different numbers of species and reactions, and the data might not even be common for the same reactions between them, and so it can be quite confusing. And so we do need tools to be able to analyze our mechanisms. And I suppose ideally, over time, we should all be converging to the same one. We should be getting closer up this hierarchy to the perfect fidelity model. By the way, I mean to say, if anyone's got any questions, do feel free to ask as we're going along. I'm not sure how good I'll be at looking around everyone, but do feel free to ask. So this is, right, we've now finally got to my introduction to the course. This is basically the narrative of the lectures, kind of in reverse. So what I'm saying is that we need to develop low-carbon fuel systems. We might then want to simulate practical combustion devices to use those effectively, because there will have to be changes. And to do that is going to require coupling of chemistry to turbulent flows. So the chemistry must be robust, because we want to be able to extrapolate, because we want to use the model in our design process for new conditions that we haven't tested experimentally. So we need it to be able to predict ignition, extinction, flame propagation, emissions, all of these kind of combustion features. But it also must be compact, because otherwise CFD models are just going to tell us to get lost. Okay, so in putting together the mechanism, we're going to need detailed chemical mechanisms. So how do we build a mechanism for new fuels is an interesting question. We're going to need to populate those models with parameters. And some of them have a lot of parameters, as I've mentioned already. But also, more importantly, we need to test the validity of these models. So are they fit for purpose? Do they give us at least good representation of any fundamental experiments that we've done? Okay, so some of you might be working in that area. And then we're probably likely going to need to reduce the model to allow it to be coupled with 3D flows or even 3D turbulent flows. Okay, so this is actually an area that I've worked in, but still a challenge, because we really need to get down to small numbers of species to be able to be used in turbulent CFD. So at this point, I just want to get a feel for what everyone's doing out there. Is anyone working in turbulent CFD? Oh, good. So, because yes, Thierry made you come here, right? I think, because my fear was that all the kinetics people would come here and all the turbulent people would go there, and really what we should have done was the other way around. But okay, is there anyone working in constructing chemical mechanisms, that kind of area? Oh, a few people. Good. This is my fear. Anyone working on sort of quantum chemistry type applications? Uh-oh. Okay, I'm going to pass all those questions to you, because that's not my area, but I'm going to present on it. Anyone working on validation of models, for experiments to do validation type things? Yeah, quite a few people. Have I missed anything? Anyone else got an area that they haven't seen many hands up from over there? So what have I missed? Experimental measurements of kinetic parameters. Yeah. Yeah. Oh, that's you. Okay. Okay, so we've got a mixture of people. So my intention this week is to kind of give you an oversight of how all of these things can fit together. And it's a bit of a challenge, because I don't work in all these areas, and also there's a lot of information. So I've had to pick and choose. So today, if I ever get past introductory remarks, I'm going to talk about reaction kinetics basics. Actually, some of this will be a bit of a repetition of what happened this morning. So I'll probably rush through that. And then I'm going to talk about basics of temperature and pressure dependence of rate constants and statistical thermodynamics. Tomorrow, I'm going to briefly talk about experimental and theoretical methods for determining rate constants. And I'm also going to mention the field of multiscale informatics, which is a way of coupling those two things together in a framework where we're trying to reduce the uncertainties in rate constant data. And then, honestly, I'll be relieved to get through the first 2 days, because then I'll be moving on to things I actually do, which is developing reaction mechanisms, experimental validation of those in low temperature, high temperature regimes, through fundamental combustion experiments, and some of the challenges there. Day 4, I'm going to talk about future fuels. So, what future technologies might we be able to contribute to mitigating climate emissions. And then on day 5, this is kind of more my core area, so analysis of models using uncertainty and sensitivity methods and chemical model reduction. Okay, so we're going to go all the way from the atom to models of, I'm not going to talk about models of devices, but I'm going to talk about, in future fuels, I'm going to talk a little bit about what might be needed there. So I'm going to try and span all the scales. So I know that when you come to these summer schools, you're coming with your own research questions in mind, and you're very focused as a PhD student, that's inevitable. But this week, what I want to do is to give you a view of the whole process from one end to the other, so you can see how what you're doing fits in. Consequence of that is that I do not have active research in some of these areas, so I know more about some areas than I do about others. So you have to maybe, hopefully, bear with me. Okay, slight plug for a couple of books I was involved in that are some of the basics of this course. The Cleaner Combustion book is good. That was a part of a European project that I was involved in before we made the ridiculous decision to leave the European Union. It's not funny, and it's going to get even less funny. So this talks about alternative fuels, it talks about validation experiments, it talks about model development, so a model reduction and analysis. So there's a lot of the topics from the course will be in this book. This is a book that was co-written by myself and Thomas Turani. So this is more about the application of mathematical methods for analysing kinetic reaction mechanisms, including actually not just combustion, but also atmospheric and some biochemical systems that neither of us knew very much about. So those are two textbooks. Also, you'll find at the back of your notes quite a few pages of references. So throughout the slides, you'll see where I've taken information from a paper. I'll put the short citation, and then the list of references is at the back of the book. So I will repeat, I guess, what Professor Matlin said this morning, which is consult the primary reference. If you want more detail, if you want to check things, I've spotted one typo since I submitted the slides for printing, but there might be more. Okay, any questions at that point? So we'll get started half an hour in. So I'm going to rattle through the basics. How many of you got a chemistry degree, actually, or a chemical engineering degree? Uh-oh, okay, most of you. So as I've said, I haven't. This is probably pretty straightforward to you. But actually, let's start at the very basics. Actually, I borrowed Bill's slides, and I liked this one because I hadn't really thought about it before as a modeler. A species to me was kind of a thing with a name, and it had certain properties like lifetime in the system or reaction rate constant or thermodynamic properties, but I hadn't thought about what it actually means. And actually the fact that it means different things to different people. So if you're an experimentalist, then what a chemical species is might depend on the system that you're using. So if you're using chromatography to measure your species concentration, then your species is that peak in the chromatogram that elutes at a certain time and that you then compare with reference data to calculate concentration. If you're using mass spec, then it might be whatever makes an ion of a certain mass. If you're using spectroscopy, it's whatever absorbs and fluoresces at a certain wavelength, and that actually might not even be a unique signal. So sometimes we have to use more than one method to deconvolute any interferences using two different types of detection method. Okay, so even from an experimental point of view, this is not absolutely straightforward. From a theoretician's point of view, then a species is a kind of geometric arrangement of the atoms. Okay, so OH is given as an example here. And how do we know that that's an actual species and not O and H? It's given by the arrangement of atoms and the distance between them. So that's quite a different concept, really. And those boundaries are, I guess, more specifically defined as a valley and a potential energy surface, which is what theoretically we think of as a species. So none of these species definitions are totally consistent, and if we're trying to compare models and experimental data, then we have to find ways, obviously, to make them consistent. But the concept of potential energy surface is a useful one. And what that's saying is that basically the energy of a system depends on the position of all the atoms. And we can compute this using quantum mechanics. As I say, this is not something that I'm involved in personally, but this is the fundamental way in which we might want to calculate important information about our species or about reactions that are moving through this potential energy surface. Okay, so you'll all know probably what the Boltzmann factor is. So normally, when we think of our systems, we think of them in terms of energies of having equilibrated, and that we would call a thermalized system. And so the probability of a system being at R will scale as the Boltzmann factor in this system. So E minus VR over KBT in this case. So the probability is that there's a higher probability of the system being down in the valleys of our potential energy surface. So that's why this is used as a definition of species. But then if we supply enough energy, then we might move from one valley to another, and that would be classified as a chemical reaction. Okay, so we call the value of R, the minimum in the potential energy surface, as the equilibrium structure or the geometry of a species. And even that is not exactly true, because we've got internal motions within the species that might lead to some moving around. But basically what we're trying to do is to understand how species through a reaction can get from one minimum in the surface to another. Okay, so the potential energy surface is quite important. And you can spend your almost entire life avoiding it, as I have, and then at some point you have to try and understand it. Okay, so the definition of a species being in this valley implies that we've got this dividing surface between species along kind of ridges in the potential energy surface. So if we just take the reaction A transforming to B, then that's given by the number of trajectories moving from valley A in our potential energy surface to valley B. And so in terms of calculating the rate constant, we're trying to count, basically, trajectories going across that dividing surface. And this is the basis of transition state theory. So I will be saying more about that tomorrow. We're just going to look at it in a simple way today. So, yeah, I went to New York yesterday for a little trip out. But I guess the analogy here is that if we want to know the rate of number of cars going into Manhattan, or the rate of number of trains going into Manhattan, then we count on the bridges. We don't need to know what's happening in Manhattan. It's very complicated. So we're kind of counting things going over that divide. So we don't need to know what cars are doing in the city, and that's very similar. Okay, so I'm leaving that to the side now. That was just what is a species. We want to move on now to chemical mechanism structure. So actually this, for any of you that were here this morning, this is very similar to what Professor Matalon was saying. If we're thinking about basic combustion of fuels, then we first of all look at the overall reaction equation. So I can't remember what his example was, but this is the hydrogen example. So stoichiometrically, 2 hydrogens react with oxygen to give us 2 waters. But actually, this is very rare because these are both stable molecules. And so rearranging, breaking bonds and rearranging in that simple way is not likely to happen. And in all chemical systems, really, we have intermediates being produced. And these will react with each other and other reactants in the system to give us our final products. So I've still not got a pointer. Has anyone in the class happen to have a pointer with them? Why would you? No? Okay. So this is not an elementary reaction step because we know that there are intermediates between what's on the left and what's on the right. In a full reaction mechanism, then we would include those intermediates, and therefore we would have a set of elementary reactions. And in an elementary reaction, there should be no macroscopically observable intermediate between the reactions and the products. Okay, but the overall global reaction is still useful. We can use it to define the reaction stoichiometry. So in this case, 2:1:2 describes the ratio of hydrogen to oxygen to water in this system. We can rearrange that in any way we like. So any multiple of the equation is true. And then we can give our general stoichiometric equation here, which is basically an effectively representation of this reaction. So in this case, we would have 2 hydrogens minus 1 O2 plus 2 H2O is equal to sums to 0. Okay, so we can define the general stoichiometric equation of any chemical process in a similar way. Vj is the stoichiometric coefficient here of the J species, and Aj will be the formula of the J species in the overall reaction equation. And if you're working in combustion, then we're not always working at stoichiometric conditions. So under stoichiometric conditions, we have just enough oxidizer available to completely burn the fuel. So if it's a hydrocarbon fuel, then we form CO2 and water. If it's a hydrogen fuel, then we're just forming water as a product. And the stoichiometric coefficients of different fuels are, of course, dependent on the number of carbons and the number of hydrogens in the molecule. So for the case of methane, we need 2 oxygens for each methane molecule that we're burning. For the case of propane, we've got 5, and we're producing 3 CO2 and 4 waters. Okay, so we can define the air-fuel ratio under stoichiometric conditions for a system. We probably use both of these. The air-fuel ratio is just the mass of air over the mass of fuel. The fuel-to-air ratio is just the inverse of that. And then, rather than specifying the specific stoichiometry, we use the term equivalence ratio. And what that is telling us, in the case of the fuel-to-air ratio, in this case, is the actual stoichiometry divided by the stoichiometric value. Okay, so if the equivalence ratio is 1, then we have stoichiometric conditions. If it's less than 1, then we have an excess of oxidizer, and we've got lean conditions. If it's greater than 1, we have rich conditions. And so this comes in if we're trying to validate our models and we're trying to develop robust models, because it's another set of conditions that we need to test over. Is our model good at representing combustion from all the way to from very lean conditions to very rich conditions? Because in diffusion flames, for example, or even in gas turbines, we might have a range of stoichiometries in our system, and we need to ensure that our model is good over the whole range of stoichiometries. So this, I guess, adds more work to those people who are doing experiments for model validation, because then you have to do your experiments not only at different temperatures and pressures, but also different equivalence ratios. Okay, so I guess the idea here is that, you know, we can do sort of several equivalence ratios with gaps in between, and if our model is good at those conditions, then it should be good to interpolate in between. Okay, the second basic thing I want to talk about is time dependence of our system. Again, this is kind of, I think, probably repeating something that was explained this morning. So more often than not, we're solving the time dependence of our chemical model. In this case, I'm just looking at an isothermal chemical system. So we've got constant temperature in a well-mixed vessel, and the rate of change of the mass or molar concentration with time is equal to the reaction rate multiplied by stoichiometric factor there. So the reaction rate is given by this simple product. So we've got each species that's involved in the stoichiometric coefficient multiplied by the reaction rate coefficient. And that can be first order, second order, or third order in combustion systems. Okay, so the stoichiometry of the overall reaction might change. K, however, although I've written it as, I guess it's written as a scalar there, but actually it can be temperature and pressure dependent. And so it's actually not, I guess, a constant. And so the correct term to use here is rate coefficient, really, rather than rate constant. Some rate coefficients only have a single value, and they're not temperature and pressure dependent, but that is actually quite unusual in combustion. So rate coefficient would be the right term to use there. The reaction order is given by the exponent Aj. So exponent Aj gives the reaction order with respect to species Aj, and the sum of those exponents will give the reaction order. So in the case of the reaction that I put up before, we've got H2 plus O2 going to water. We can't really use this because this is not an elementary reaction. This is a global reaction step. But if we have elementary reaction steps, then we can use this term, and the reaction order and the stoichiometric coefficient would be mathematically the same. Okay, so let's look at the hydrogen system. This is a sort of snapshot, really. The overall mechanism is a bit more complicated than this. But you can see here that the initiation reaction here, where we've got two molecules reacting together, will give us one reactive radical and one slightly less reactive radical, H plus HO2. Okay, so that should be an elementary reaction of order 2. Then hydrogen can react with oxygen to give us two radicals. And this is what we call the chain branching reaction, because we are converting one radical to two, and that is kind of accelerating the reactivity of the system, because that OH can then go on to react with hydrogen, so we're consuming more of the starting fuel. Okay, so for these elementary reactions, we can use the stoichiometric coefficients to give us a reaction order. So the reaction order is 2. What about this one? We've got 3 things on the left here. And so we've got the third body, M, which is involved in collisional processes in that reaction. And so the reaction order in that case is 3. Question to you guys, is that a termolecular reaction? And you have to shout. You think it is? Anyone think it isn't? So this is debatable, actually, because strictly speaking, a termolecular reaction should involve chemistry and not just collisions. I will say that this is not a termolecular reaction now, and then later on I'll give you some examples where kineticists who are cleverer than me are coming up with termolecular reactions that we've been told for decades don't exist. So it's actually very hard for 3 molecules to react chemically together by breaking bonds, etc. So normally this reaction would not, it would be considered third order. Okay, so the rate constant will, the overall rate of reaction will depend on the concentration of these 3 reactants, but not considered termolecular. Okay, because M is not really involved chemically. Okay, so I'll say that now, but then I will give you some examples later where there is new work that shows that there is some termolecular chemistry. I don't know, I might be saying something before it actually comes up on the slides. Okay, so each elementary reaction step then can be characterized by the stoichiometric equation. So the stoichiometric coefficients on the left-hand side and the right-hand side should be distinguished from each other, I suppose. And we can get the overall stoichiometric coefficient belonging to a species I by subtracting the left from the right. So in that reaction involving M, it's on both the left and the right, so it's not consumed in that reaction. Okay, so the left-hand side ones should be positive integers. And actually on the right-hand side, they can be positive or negative integers depending on the type of reaction. Okay, so the overall stoichiometric coefficients can also be any number, positive or negative. Let's just move on then to how this fits into basic reactions for reactors. So in terms of chemistry, the simplest way to look at a chemical system is in a well-mixed system, and then we can just set up an ordinary differential equation, And that's quite useful, for example, for looking at jet stirred reactors where we have good mixing. But actually also, I'm not sure how far Professor Martin is going to get with numerical techniques, but quite often in a CFD model, we actually split the chemistry from the rest of the solver. And so in fact, in a grid cell, we are just solving basic ODE type equations because we're assuming that the grid cell is well mixed and we solve the chemical steps separately. Not always, but that is one method of including chemistry in a CFD model. Okay, so even for CFD, it's important to kind of know about ordinary differential equations. So the problem with including these equations in CFD is that we have an equation for every single species. And so if you're thinking about, I don't know, 1 million grid cells in your CFD model, it's like solving chemical rate equations for 1 million reactors. So that's problematic, and it means that if we don't do anything about it, solving these ODEs for the chemistry will consume an awful lot of the computational time in our reactive flow model. And one of the issues there is that the tendency then is to go, oh, well, the chemistry is too complex, so I'll just put in this nice one-step global scheme because that will mean I've only got 2 species or maybe 3 species involved. And so that's a lot less equations to solve. But the problem is there then, if we're not clever about how we do that, we lose information about the intermediates, and that might be really important in terms of solving the dynamics of the chemistry in our system. Okay, so we need to find clever ways, basically, of solving these ordinary differential equations that represent the rate of change of species according to the reaction rates. Okay, so in this equation, we've got the rate of change of a molar concentration or a mass concentration with time as a function of the reaction rates on the right-hand side. Okay, and if for large systems, that leads to a large set of coupled differential equations that we have to solve. And we also potentially, if we're solving for temperature, then we also have an energy equation as well. Okay, so in this case, we need information on the heats of reaction, and we also need information on heat transfer in our system. Okay, so if you're solving for a jet stirred reactor, for example, then actually these things are important in terms of comparing your model with the experimental data that you're collecting. Okay, so notice here then we're going to need a lot of information about the reaction rates, and that involves understanding the rate constants for each of the reactions in our system. And if we want to model heat release, then we also need enthalpies for the reaction as well, and so that involves determining thermodynamic information. At the time. Okay, and then so say we've got our system of ODEs, we've got to solve it. I mean, I'm not going to go into numerical methods, but most of them involve some kind of manipulation of what we call the Jacobian matrix for our system. And the Jacobian matrix is given by the partial derivative of the right-hand side of our ordinary differential equations, given by f as a function of concentration and the rate constants here. So the partial derivative of f with respect to y, the concentration. Okay, so this will be a matrix that will be the size of number of species times number of species. Okay, so why is this important? Well, it's important because most solvers have to invert that Jacobian matrix as part of the solution technique. And so the larger it is, the harder a task that is. And there are some solvers that can do clever things to invert large matrices and can also exploit the fact that a lot of entries in that matrix will actually be 0. But nevertheless, we have to do something with that matrix to solve initial value problems like the one I've just given you on the last slide. Where's my cursor gone? I really need a pointer. Anyway, the point is basically the effort will scale in solving the system. If we cannot find clever methods, we'll solve as a number of species squared. Okay, so if you go from 8 species in the hydrogen reaction system to 30 species in methane, then I wish I hadn't picked that now because I can't scale that up in my head. But basically, that's that's a huge difference in terms of the computational effort. And this is why model reduction and clever numerical methods are quite important, really, in actually utilizing the chemistry models that we're developing. If we can reduce a methane model from, say, 50 species down to 20 species, then that's going to give us, let's see, what's that? It's going to give us about a factor of 8 speed up. So it's really worth doing. And the reason is because of the need to manipulate this Jacobian matrix. Okay, I'm sure you can all do this, so I'm not going to dwell on this, but I've just given a little example here of that simple hydrogen system, and the rates of reaction are given on the right there. So we've got the rate coefficient multiplied by the concentrations. Okay, so all of those reactions are bimolecular apart from R5, which is third order, but it's not termolecular unless there is some chemistry involving that third body species M. Okay, and then if we want to set up our system of equations, I'm sure you all know how to do this, but basically, if we look, for example, at the hydrogen radical, the rate of change of hydrogen concentration by dt is given by summing all the reactions that form hydrogen, summing the rates of those, minus the rates of consumption reactions for hydrogen. So just make sure that you understand that for a simple system. I mean, the truth is these days, we all use ChemKin, Cantera, FlameMaster, etc. We never sit and write these equations down anymore, do we? But it is important to know what's behind the solvers that you're using. Okay, that was well-mixed systems, and in a well-mixed closed system, then we do expect everything to sort of trundle along to equilibrium at different rates of change. We'll come back to that later. In open systems, this is actually what I spent some of my PhD looking at, actually. These are kind of fun because actually there are cases where you don't actually reach equilibrium. You might end up flowing reactants in and with products flowing out in such a way that you can get oscillations within your system. And actually, why is that useful? I don't know. It was fun. I don't know but it's actually useful because it's a pretty tricky test of your model. If you can reproduce this kind of oscillatory behavior in a reaction system, then it shows that you've got a fairly good representation of the chemistry over broad sets of temperatures and concentrations. So it might be constant pressure, but you are varying the other quantities. And in this system, the main difference, here we go. The main difference here is that now we have an extra term which represents the inflow of new reactants and the outflow of products. Okay, and this will depend on the residence time for the reactor. Okay, so actually, what does that mean? It's not something that we can measure that easily. It sort of represents the mean time that the fluid is going to, that the species is going to spend in the reactor. The likelihood is it's a distribution, but we represent it by a single value, I guess, for ease. And then we've got an extension of the equation for energy, now including a term involving the specific heat and the residence time. Okay, so now we've got a new thermodynamic property that we need to include in our models. Okay, so I mention it really just because I spent some of my life doing it, but also because I think it is a very good validation test. So this is an example from some oscillations in a wet carbon monoxide system, and actually, depending on the reactor conditions and residence times, starting temperatures, you can get quite different profiles. So either nice periodic system, or you can get these sharp ignition events followed by the inflow of reactant, followed by a rapid ignition, etc. So if your model can represent all of those different conditions, then you're showing a kind of robustness in the model. Okay, we're just about 5 minutes off the break, but I want to start the next section. Okay, we'll start the next section. Waste 5 minutes. So we're developing our reaction models, and we have to populate them as well as we can to represent those reaction rates. So we need rate coefficients, and depending on the type of reaction, they can be temperature dependent or they can be temperature and pressure dependent, or maybe they just depend on collision frequencies. It depends on the type of reaction. So for temperature dependent rate coefficients, Arrhenius, you've all heard of Arrhenius, have you? Yeah. Actually, just as an aside, did you know that Arrhenius actually predicted for a doubling of CO2 in the atmosphere of 4-degree change in global surface temperatures in the middle of the 19th century? Did everyone know that? So actually, he was a climate scientist too. Nobody listened, of course. So Arrhenius argued that for reactors to transform into products, they need that minimum amount of energy called the activation energy. So if we go back to the earlier things I was saying, this is about the energy required to get our species out of one well over the ridge in our potential energy surface and into the well that represents products. And that's why it's kind of useful, I think, to think of species in that way. If we think about the reaction between molecules A and B and the potential energy changes in the reaction. So the reaction starts when the molecules collide and interact, and they can exchange momentum and energy, but they can also, bonds can be broken and they can exchange atoms. So usually in an elementary reaction, we have this transition state, not always. Oh man, where's the cursor gone? Transition state in the potential energy surface, and if we have enough energy, then the system can reach that maximum, and a small increase in energy can then push it over in the direction of the products where potential energy falls again, and it falls into this new equilibrium in the products well. And so the height of that can be described by the activation energy. So at a given temperature, the fraction of molecules with enough kinetic energy to overcome that well, so greater than the activation energy E, can be calculated from statistical mechanics. So if we assume that we've got a Maxwell-Boltzmann distribution, then we can calculate that fraction. So what that means is that that basically we've got this thermodynamic equilibrium. Okay, so we have got a kind of separation of the exchange of energy from the chemistry. So there are cases where that isn't true, where we've got these things happening on similar timescales, but normally we assume that this equilibrium is reached quite quickly. Okay. So the Maxwell-Boltzmann distribution describes particle speeds where the particles, gases, are moving freely without interacting except for these brief collisions where they're exchanging energy and momentum, and then they reach thermodynamic equilibrium. Okay. So I'll talk a bit later on about non-equilibrated systems. Okay. Also important is the orientation. So collision theory then, the original references here suggest that molecules can react if they collide with a relative kinetic energy along their center that exceeds the activation energy. So just the example I've given on the right here for NO and NO3. Certain orientations are ineffective because we don't have proximity of the right atoms to achieve the chemical part of the reaction. And then we've got the bottom one here where both the orientation and the energy levels are effective to give us the reaction to form our products. Okay, so we've got then basically only a fraction of the total collisions that will have the sufficient energy and the right orientation to give us our products. And so that leads us to the extended Arrhenius equation that looks something like this. Okay, so it's just a schematic of requiring sufficient energy to overcome that barrier to move from species A to species B. And we can see that basically that's very temperature dependent, because if we look at this distribution of the Boltzmann energies here, the activation energy is here. If we change the temperature from T1 to T2, then we have more molecules in the system that are above that threshold and able to react. So that's why, obviously, increasing the temperature, we're likely, not always, but we're likely to increase the reaction rate. Okay, so, sorry, just keeping an eye on time. So I think, actually, we just take a break now because we've been going an hour. So maybe it wasn't the right thing to do to have started that new section. But so yeah, if we can start again at 1:15. Any case, this first slide is really just a confirmation of things I've already said. So I'll start at the bottom. In transition state theory, we have this assumption that we've got this activated complex formed at the, I think it's probably easier just to use, at the top of the barrier here, but that actually this is not a long-lived species. Okay, so this transition state species is considered to be in equilibrium with the starting reactants, or is going to thermalize very quickly. So what this is saying is it's going to reach a Boltzmann distribution very quickly. And in simple systems, we don't have this crossover between the collision timescales and the chemical reaction timescales. But I will show you some examples of where that assumption is challenged later. But if we have this rapid thermalization, then we can specify the statistical and thermodynamic properties of this transition state, and then we can also look at the chemical reaction that takes it over into the final product state. It is the case that not all reactions have this energy barrier. So, for example, in reactions where we're not breaking a chemical bond, like the combination of atoms, there isn't an activation energy, and therefore the rate coefficient is given by the frequency of collisions between reactants. Okay, so not all reactions do have an activation energy. Okay, so in transition state theory, I'm going to say more about this. I'm going to mention master equation models tomorrow, but from the basic point of view, the rate at which the final state is attained is given by the number of activated complexes formed, and then the frequency with which they go over to the final state. And we can calculate these for simple systems using statistical mechanics, or we can use more complex methods like master equation systems that I'll talk about tomorrow. But so this sounds relatively straightforward, but unfortunately, in order to be able to do that, we need to know what the potential energy surface of our system looks like. And unfortunately, that's where we have to use quantum methods or density functional theory methods to give us that surface, or at least to give us the height of the barriers. So I'll come back to that topic later. There are a couple of really good reviews on this topic that if you're interested or you need to know more, I would encourage you to look at. One by Judith Jadot and co-workers, and one by Steve Klippenstein from his plenary lecture at the symposium, which would have been in 2016, I think. So I'll go into a lot more detail than I've gone into. I've just given you an example of a potential energy surface from the system that I actually did work on. Well, when I say that, it was actually mainly Frank and Goldsmith. But so you can see here that actually these surfaces can get very complex. This isn't even anything like the most complex surface you can look at. But this is the N-propyl plus O2 system. I'm going to be talking a bit more about low temperature chemistry as we go through. But in this system, we form the typical species that we see in low temperature ignition, which is the peroxy radical, RO2, and then the 2QOH species, and finally going out to products here. And depending on the temperature and pressure conditions, we're either going to form OH and go on to chain branching routes, or HO2 and go on to termination routes. But you can see that we've got multiple barriers and wells along the way. And so if we want to calculate rate coefficients for this system, then we need to know what that surface looks like, and we need to know what the well depths and the heights of those barriers are, and the shape of that potential energy surface. I'll come back to that system later, because one of the things that we did was look at the uncertainties in predicting rate constants via those methods. Okay. So if you're just using models, then maybe you don't think too much about where the rate data comes from. You're just looking at the Arrhenius form in a ChemChem file or in a Cantera file or whatever. Sometimes you might see the simple Arrhenius function where you don't have that extra t to the n term in the middle. And that's more true, actually, if anyone's working on either atmospheric chemistry or liquid phase chemistry, where we've got a more limited range of temperature conditions. So here we've got the pre-exponential factor A and the activation energy for our reaction. And the reaction can be either endothermic or exothermic, depending on whether the products are lower or higher in energy than the reactants. If we look at this is for a sort of atmospheric chemistry system where we've got the very slow reaction of methane plus OH. So that is a reaction which is slowly breaking down methane in the atmosphere, eventually to give us CO2. But if we're plotting over atmospheric conditions, then this looks like a straight line. So this is a standard Arrhenius plot, where we're plotting the log of the rate constant against the inverse of the temperature. Okay, so Arrhenius behavior leads to a straight line in that type of plot. But if we look at the same reaction over combustion conditions, so obviously this is a key reaction in the combustion of methane, where we're pulling a hydrogen off the methane to give us the methyl radical, then we see curvature in that plot because the activation energy is slightly temperature dependent. And so that leads to the extended form of the Arrhenius equation. I mean, actually, it's different, and so we probably should use different terminology, but we normally see it looking like this, where we've just got this extra t to the n term. And it's worth remembering that basically these Arrhenius equations, they're just basically fits to data. You know, they're not, they do have a foundation in an understanding of the energy barriers and collision frequencies, etc. But at the end of the day, if you're doing kinetics experiments, then you're just fitting this Arrhenius expressions to your experimental data. Okay, so the t to the n term comes in because we might see activation energies which are slightly dependent on temperature. Okay, so we might see from this because we've got quantum effects like quantum tunneling, or we might see internal modes like vibrations or rotations changing the nature of the reaction movement through the potential energy surface. So this is the standard form, but sometimes you don't see activation energy at all, and sometimes you just see the simple form of the Arrhenius expression with no n. So n would just be 0, basically, in some of the mechanisms. Other times we see more complicated temperature dependence of our rate coefficient. So classic reaction that's been debated over recent years is okay, don't know what that means. This reaction between HO2 and OH, and it's important in the hydrogen oxidation system, but it's also important in other combustion systems because the hydrogen system is a kind of fundamental core of all combustion systems. And so here we see this change in slope actually of the activation energy for that reaction. I'll come back to it later as to why that's the case, but we've clearly got two different routes here from reactants to products with different temperature dependence. And so in a mechanism, then you would see this declared as a duplicate reaction, and the way in which this is expressed as a fit is as a sum of two Arrhenius expressions. Okay, so I don't know if anyone's come across these duplicate-type reactions in any models that they're using. No? Yeah, a few people have. Okay, so like I say, I'll come back to this reaction later because trying to find consistency for the different sets of data and theoretical calculations that were available for this reaction was actually quite challenging. And it's one of the cases where multiscale informatics has been useful, where tried to combine different sources of information to try and get some kind of optimization where we've got consistency between the different data sources. Yeah.
So there are two Arrhenius expressions throughout the system?
No, it doesn't. It means that there are two potential pathways through the potential energy surface. So there could be different wells and barrier heights, or the reaction might skip over a well, for example. Yeah. Okay, so we also see pressure-dependent rate coefficients in our mechanisms, and model reactions like isomerization, for example, are types of reactions that could be pressure dependent. So the classic one, sorry, I don't know why that's doing that. I think it might be. I'm not sure what to do. Turn off the sound. If we've got a reaction like an isomerization, here the example is cyclopropane, where we've got some rearrangement of the atoms in the molecule to give us propene. So experimentally, the rate coefficient was found to be first order and pressure independent at high pressures, but second order and linearly dependent on pressure at low pressures. Okay, so this is going back quite a long way. And the interpretation, going back all the way to Lindemann and Hinshelwood, if those names mean anything, was that molecules of cyclopropane are colliding with other molecules in the system, which we represent as that third body M in our reactions. And that was producing vibrationally excited cyclopropane molecules. So we call that C star. And these molecules that have this extra energy through collisions can then isomerize by transforming into another molecule with the same atoms but with a different arrangement. The collision, so the excited molecule can either go on to form products, or it can kind of de-excite and go back to the reactants. And so the rate of overall reaction will depend on which of these is winning out. Okay, so later the theory sort of developed, and it was shown that these collisions can create excited reactant species with quite a broad range of vibrational energies. And so the cyclopropane molecule is kind of moving up and down an energy ladder. And the rate coefficient is going to depend on the energy of the excited reactant. Other examples of this system that might be more important to us as combustion scientists, so decomposition of hydrogen peroxide is an important one. So collisions are moving this, that molecule up and down the energy ladder. Under some situations, there's enough energy for it to move to products, which is 2OH in this case. Methyl radical plus OH is another one where we're forming CH2 and water as products. So for the case of H2O2, got collisions with any other reactant that's present in the mixture that might lead to changes in row vibrational energy up and down this ladder. So that could be large molecules, it could be nitrogen if we're in an air system, it could be water which is formed as a product from the reaction. And molecules with an energy level higher than the threshold will then decompose to give us OH. So that's going to depend on the pressure, because the number of collisions that occur will depend on the concentration of M. Okay, so at higher pressures, obviously, we've got higher concentration of that third body. What's the example I've got here? So this is the methane decomposing to give us methyl plus H. So in this case, we've got a bath gas in an experiment which is helium. So collisions with helium are inducing transitions up and down the energy ladder. This is an example that Steve gave in his lecture from the paper in 2017. And occasionally we get enough excitations for the internal energy to exceed this threshold for dissociation, forming our products. But this is always going to be in competition with collisions which are either going to further excite the molecule or will de-excite it back towards methane, which is below the dissociation threshold. So we've always got this competition between dissociation and collisional excitation or de-excitation, and that's going to determine the pressure dependence for the reaction. Okay, so if we're in the low pressure limit for the reaction, then every molecule that's above the dissociation threshold is going to dissociate. And so in that case, the rate of dissociation is determined by the rate of exciting molecules above the threshold. Okay, so that's going to be dependent on the number of collisions, which depends on the concentration of our third bodies, and thus depends on pressure. Okay, so in the low pressure limit, we get this pressure dependence. In the high pressure limit, molecules are going to undergo collisions even after they're excited above the dissociation threshold. So we get a Boltzmann distribution here, we get a thermalized system, and the rate coefficient now is going to be independent of pressure. Okay, so in this case, the rate constant will reduce to a Boltzmann average of the microcanonical dissociation rates. So that means the dissociation rates which are specific to each energy level in the system. So we can sort of understand the low pressure limit and the high pressure limit for this reaction, but in between we've got this complicated function where we've got this competition between dissociation and collisional energy transfer, and that leads to the need to kind of find a method to define that pressure dependence. So again, we're going back quite a long way here, but originally from Lindemann, we have a simple function which tries to connect the low pressure limit to the high pressure rate coefficient, giving us an apparent first order rate coefficient for any pressure in between. Okay, so what we call this region the fall off region. I've got a plot coming up which shows you what that might look like for examples in a minute. So in order to calculate this, we need to know the low and the high pressure limiting cases, and then we've got this functional dependence to give us our blend in between those two cases. Okay, so go back to here. In this equation, then, we've got the reduced pressure PR, and we've got this function F. In the Lindemann approach, the simple approach, F is equal to 1, and the reduced pressure is given by the ratio of the low pressure rate coefficient to the high pressure rate coefficient multiplied by the concentration of our third body. So this concentration is obviously pressure dependent. Another thing to kind of pay attention to is that not all molecules are equal in their contribution to collision efficiencies. And so we need to know really what the effectiveness of different species are. So you might see in mechanisms when you're looking, say, for example, at the Aramco scheme for methane, you've got different efficiencies. Nitrogen is commonly used as a bath gas in experiments, and so and it's also obviously a major component of air. So the general assumption is that nitrogen has an efficiency of 1, and everything else is represented relative to that. So I think I'm pretty sure this comes from an early version of the Aramco scheme, okay, where the third body is quite complicated because you've got water in the system, you've got hydrogen peroxide, oxygen, in this case argon, helium, and they've each got different efficiencies. So we've got higher efficiency for water and for hydrogen peroxide, and lower efficiencies for inert gases like helium in the system. Okay, so this is the sort of standard method for representing overall collision efficiencies of our system. I don't know if any of you have been keeping up with the webinar series that the Combustion Institute has been putting out. Any of you? Oh, that's disappointing. So I think it was a COVID thing, actually, to start with. But I think to kind of try and keep people connected, I don't know who organised them, but basically there was monthly seminars on YouTube, or they were live and then on YouTube. So you can go back and watch some of these again on different topics. It's really excellent, hour-long presentation series. But Mike Burt gave one, actually, on this topic. And he was questioning the use of these simple linear mixture rules that we're pretty used to using, and suggested that actually the sums of efficiencies should be based on reduced pressure and not standard concentrations that we normally use. So I think that's an ongoing topic about how well we are representing these collision efficiencies of different molecules in our system. So they may, for example, be even temperature dependent, and it's just not something that we look into very often. Okay, so the general trend is that larger molecules with more excitable frequencies will have larger efficiency factors. So water, for example, and hydrogen peroxide, as you saw, had quite high collision efficiencies compared to inert gases like helium. Okay, so this is something, I don't know if any of you do sensitivity analysis. Hands up who's ever applied. Okay, good, some people. Would you ever have thought about looking at third body efficiencies as part of the uncertainties in your system? Not necessarily. I mean, I've done a lot of work on sensitivity analysis and not really looked at this in detail, or as much detail as I should have. But you know, any uncertainties in these efficiency factors will lead to overall model uncertainties. There's been some recent work by Aaron Jasper, who looked at, he carried out a theoretical study of efficiencies for hydrocarbon collisions and looked at different types of hydrocarbons, linear, branch, cyclic, alkanes, alkenes, alkyl radicals, etc., with different third bodies. And he's kind of extracted some trends with respect to the chemical structure and the number of carbon atoms in the system. So that's potentially a way forward for determining more accurate values. I mean, otherwise, then you have to do kinetics experiments with different bath gases and determine different efficiencies that way. But it's a lot of work, actually, to do that. That's another variable in your experimental system to look at. Okay, so I think this is a topic that will be ongoing for a while, how to best represent third bodies in our system. So probably historically, you're used to seeing Troe formulation if you're used to working with mechanism files. So in this case, so the Lindemann approach, F was assumed to be 1, but in the Troe formulation was an improvement on that. Then we've got a more complicated expression describing the functionality of F as a function of the reduced pressure and also temperature. So if you've got a mechanism that's got a Troe formulation in there, then you'll see an extra 4 parameters related to alpha and temperature, which represents the fall-off curve. Okay, so I've got 2 examples here. Okay, so we've got basically, hopefully you can see that. We've got the low pressure limit and the high pressure limit given here, and then a comparison between the Lindemann model where we've got F is equal to 1 and the Troe parameterization, which is giving this fall-off curve here. So there is a slight difference there. Some systems the difference is much larger, or maybe we don't even reach the high pressure limit under conditions that we would normally look at. Okay, so this is a way of representing pressure dependence in our mechanisms that you're probably used to seeing, I would think. Complex forming bimolecular reactions might also be pressure dependent due to losing extra energy in collisions leading to thermal equilibration. So CH3 plus OH forming a complex and then going on to form products, CH2 and water is one example. And the Troe formulation was shown to accurately represent the fall-off region for some of these reactions. But for reactions with multiple wells in the potential energy surface, there's been work which has shown that there's quite large errors in the Trowy fit that can get as high as 40%. And so that, I guess probably in the last decade, there have been some efforts to come up with new ways of representing pressure dependence for some reactions where the Trowy fit might be in error. So I don't know if any of you have come across the P-log formulation. Yeah, some people. Oh, not many actually, that's surprising. So the P-log formulation actually is just really an interpolation method. So in the mechanism where you've got this P-log formulation for pressure-dependent reactions, then you're defining an Arrhenius expression at various different pressures, and then using this interpolation function for pressures in between. So you might define an Arrhenius expression curve here, and one here for a different pressure, and one here, and then you're using interpolation using the equation on the left here to give you the rate constant at pressures in between. I guess the issue here is then how do we represent third body efficiencies in the P-log formulation? So I think that's a challenge that has yet to be overcome, in fact, in a consistent way. And so in some mechanisms, you might see a mixture of a Trowy type expression and a P-log expression. And you might, I guess, use a Trowy expression if you want detail on third body efficiencies. So I think this is a topic that's going to be ongoing. One of the other problems with the P-log formulation that I've discovered in recent weeks is that actually if you start to do CFD and you like using OpenFOAM or something like that, then a lot of these formulations haven't been included. So you can do this in ChemKin and you can do it in Cantera, but you can't do it in all codes actually. So that means that mechanisms using the P-log formulation might be tricky to use in some CFD codes. The other way of doing this is using Chebyshev polynomials, so they can be used for fitting pressure dependence of rate coefficients. So some of the codes that are used for predicting rate constants, like the master equation codes, will give you Chebyshev polynomials as an output. The problem with polynomials is that they're fitted over a specific range of conditions, and then when you start to extrapolate them outside of that region, wild things can happen. So you've got to be very careful if you're using Chebyshev polynomials that the fit is over the range where you plan to apply your model, so you don't have these extrapolation issues. Okay, so in summary then, that's three different ways you can represent pressure dependence. The Trowy fall-off type expressions, which are giving you that fall-off curve as a function of reduced pressure. The Chebyshev polynomials, which are just polynomial fits really of the pressure dependence, but you've got to be careful with extrapolation. And then the P-log functions, which probably, if you haven't got complicated sets of third bodies, are a good way to give you the fit, but we've got challenges in how to represent different colliders in that formulation. Just as a question, how many of you are kind of using chemical mechanisms in your modeling? So quite a lot of you, yeah. So here's another question, do you actually look at the mechanism and go, oh yeah, this is the pressure dependent reaction, this is where it came from, is that a good source for that data? Oh, you're all laughing. Okay, that's good. Okay, so you're basically going, okay, I trust this group, I take their model, right? Yeah, that's, I mean, yeah, that's good. So, no, I mean, it's very understandable, right? You've got a lot of other work to do. You don't want to necessarily worry about each reaction individually. Okay, but that's good to know. So when you get home, have a look at the mechanisms you're using and look at the formulations, particularly the pressure-dependent reactions, just so that you are aware what's in there. Okay, so don't worry about this particular issue for now. But I shouldn't say this because I'm being videoed, but basically kineticists, they do like to look for more complexities, right? They want to make the modelers' lives more difficult by going, oh, so just when you thought you'd nailed this, now we're going to tell you that after all these years of saying there was no chemically intermolecular reactions, we found some. Thus providing difficulties really of representing some of this behavior in simple model setups. But so just over the last few years, after me telling you and physical chemistry textbooks telling you that there aren't really chemically intermolecular reactions of potential importance in combustion, Mike Burke and Steve Klippenstein and other people are now saying, oh, but there is. So here we've got systems where we've basically got a kind of crossover between the collisional energy transfer and the chemical reaction part of our system. So we've got reacting molecules that have non-thermal distributions. So these are molecules that have not equilibrated back to a nice Boltzmann distribution. Okay, so that can give us chemically intermolecular reactions, and they are suggesting that this is of potential importance in combustion now. So we've got reactive collisions which are occurring on similar timescales as the thermalization or the equilibration. Okay, so this is something that we're taught in textbooks that shouldn't happen. In this case, this M no longer becomes the right way to think about this reaction. So M is basically something which is the same on the left of the reaction to being on the right of the reaction. It doesn't go through any chemical changes. It's just exchanging energy through collisions. But now they're saying that basically we can have reactions where instead of R plus X plus M, we've got R plus X plus Y. And actually, our third body is no longer chemically inert and can take part in the reaction. Okay, so examples that they're giving are H plus N 2 plus O, which would be important in maybe in NOx formation in our systems. H plus CO plus H, so important in syngas combustion. H plus C2H2 plus O2. Okay, so there are reactions that potentially might be important in our combustion models. And what it's saying is basically increasing the pressure increases the heat transfer rate between the reacting molecules. So maybe at high pressures this is not quite so important. But a lot of the experiments that we do are actually being carried out at low pressures. And so it might be of importance for interpreting those types of experiments. Also, they are showing, I think this is, pretty sure this is, oh no, this is 5 atmospheres. So this is actually a flame prediction at 5 atmospheres, so that's not a low pressure. And what they're suggesting is that you do see a difference in the predicted flame speeds for this system. This is a hydrogen-oxygen flame if we account for H plus O2 plus R in this system. So R in this system can be any of the radicals H, O, OH. Okay, so this is a termolecular reaction now that's giving us, I'm trying to look at the units here, maybe 20, 30 centimeters per second difference in the predicted flame speeds. Okay, so in this plot here, obviously the symbols are the experimental data. Then we've got the difference between including these as termolecular reactions or not, and then we've got the flux through that reaction plotted on here, which is given in the scale on the right-hand side there. Okay, so sorry, it's not the flux, it's the peak fraction. Oh yes, it is the reaction flux. So it's the peak fraction of that HO2 plus R reaction through, where R is H, O, or OH. Okay, so that, it does look relatively significant. But it's, I'm trying to think what would happen if you put, if you're even able to parameterize this and put this into ChemCon. Is it going to tell you can you have 3 reactants on the left? I haven't run a ChemCon model myself for a long time, so can you have 3 reactants on the left? I guess you can. Not sure. So that's just a complexity that might crop up in certain situations. And so I think that's a story that will continue as well. So I'm trying to give you a flavor of kind of things that are emerging from the kinetics community. So these different ways of representing pressure dependence and also potentially reactants that, that don't thermalize and that give us truly thermomolecular reactions. Okay. Just let me check the, yeah. Sorry, I can't quite hear.
What would be an example of a convolution kinetics, which at low pressure? Because when I think of rapid changes, I'm thinking.
Well, that was, I mean, so, yeah, I'm not quite sure I quite understand your question. I mean, this is an example, this reaction H plus O2, you know, H plus O2 plus M is fundamental to all combustion. Well, I don't know if it's been tested across a whole range of applications, but I think if you do sensitivity analysis of any system, H plus O2 will come up as being a fundamental reaction. So it's ubiquitous. Even in hydrocarbon combustion, it comes up at higher temperatures. You know, it's a fundamental foundation. Now, and they're saying that basically it has the potential under some conditions to behave in this way. And they're giving you an example. I mean, I don't know how many sets of conditions they've actually modeled to see how important this is, right? You'd have to look across lots of different systems because this reaction is in all models of combustion. So it's a bit hard to answer that. It's a good question, but it's a bit hard to answer the question. My guess is that they've picked out an application where you do see a difference, so they can include it in the paper. But whether that would be true at very high pressures, I don't know. I suspect the higher the pressure, the less important these effects might be. So I'm not sure we have enough information to answer your question. Email Steve Clipperstein and ask him. Okay. So I was going to move on to say something about thermodynamics and thermochemistry, just basic stuff, but I don't know if I might rush through this because I'm suspecting you probably all know the basics here, and those people that were in the lectures this morning will have already heard about this. But basically, I'm coming at it from the perspective of, you know, what are these basic thermodynamic quantities, and well, why are they important in our combustion models, and also how do we obtain data for them, and what errors might that lead to in our system? Okay, so I'm not going to dwell too much on the basic quantities, so I'm fairly sure you all know this. So enthalpy is a really important one for us because we need to know the enthalpy change in our reaction. That's going to give us the heat of reaction. We can't measure the enthalpy of a species directly. We have to measure the enthalpy change of a system. As was explained this morning, generally in combustion systems, we represent these as a fit, as a function of temperature using polynomial type fit, so using NASA polynomials. So the actual NASA polynomial itself is really just a fit to the best available data. So the important thing here, I suppose, is what is the best available data? So again, I mean, have you all come across Burkhart's database for thermodynamic quantities? Or this is your therm.imp if you're running ChemKin. But again, do you look at where this data's come from? No. So there are many ways of obtaining this information, some of which have, you know, higher levels of accuracy than other methods. And the databases that you're using will contain data from lots of different sources. I mean, I'm not entirely sure how often the Burkhart database is now updated, but up until fairly recently, it was updated fairly often. And so as new information comes out about a species, you know, the entry or the polynomial will be refit and the entry will be updated in the database. So it's always important to check the latest data because, you know, you might be using a therm.imp file that came from the 1980s. You really don't want to be doing that. So it's important to know where the data's come from, and that's a little bit what I want to cover over the next part of the lectures. Okay, why is it important? Well, we might want to calculate the enthalpy of our reaction, so that's important because we might want to know what the heat release is. If you remember, the enthalpy of reaction was in the energy equation that we might want to solve for our system if it's non-isothermal. Okay, so this data is actually really important. And just to kind of repeat, I guess, what was said this morning, normally we would look at the standard enthalpy of change of formation for a species. Typically, a reference temperature would be 298 Kelvin. So an example here is, enthalpy of formation for methane, minus 74.8 kilojoules per mole. Okay, so for small species, we tend to have very good data on these basic quantities. But for larger species, not so much. So it really just depends on the system that you're modeling as to how good the data is going to be for some of these quantities. I just put this in as an example, as a real-world example of why this might be important. For fuels, if you're an engineer working on something like burner design or whatever, then you're looking at the heating value of a fuel. And if you're thinking about switching fuels for your system, then this might be something that you want to look at. And actually, the lower heating value comes from knowing the standard heat of formation for species. So the lower heating value for a hydrocarbon species with X carbons and Y hydrogens is given by this equation. So the stoichiometry of CO2 multiplied by the heat of formation there, and the same for water as a gas, I'll explain why that is in a minute, minus the heat of formation at 298 of the fuel. So this is a lower heating value because we're looking at steam, so we're looking at the vapor form for the water produced here. If we can manage to recover some of that energy by condensing that steam back to a liquid, then we will get the higher heating value, we get higher efficiency from our system. So as an aside, then condensing boilers are operating in that way, right? Which is why you should get higher efficiency from them. So just, the heats of formation are just important, really, just from basic engineering. And I put an example in here for natural gas versus hydrogen, because already this tells us something quite useful, I think. So in this case, we're looking at the lower heating value and the higher heating value for natural gas versus hydrogen. And we've got two different numbers. One is where we're using functions of mass, and the other it's stupid units of standard cubic feet, non-SI units that we use. But it's interesting to look at the difference, because if you look at the heating values for hydrogen versus natural gas as a function of mass, then hydrogen is much higher. But if you look using volume, then it's less than a third of what we get for natural gas. So what that tells us is for the same fuel volume transportation, we're going to get less than a third of the energy produced. And so that means that basically we're going to need to compress hydrogen. So just from looking at the heating values which come from the enthalpies, we can already learn something useful about changing fuels in our system. Okay, I will come back to hydrogen as a future fuel later in the week, but just these basic quantities are already pretty useful. Okay, if we come on to entropy. So entropy is related to the number of microstates in our system that are consistent with the macroscopic quantities that we're used to dealing with, like volume, pressure, temperature. Okay, so that's a sort of specific configuration of the thermodynamic system that has a certain probability as part of the thermal fluctuations. Okay, so we know then that the second law tells us that basically the entropy of an isolated system always increases. Okay, so we're moving towards, in a closed system, the thermodynamic equilibrium, which is the state with the maximum entropy. Okay, so That's true for a closed system. In an open system, where we can exchange heat, work, mass over boundaries, then the equation is a little bit more complicated. So the rate of change of entropy with time will be the net rate of entropy production in the system. I wish I'd done this the other way around. We've also got the net rate of entropy flow due to flows of mass in and out of the system. And then we've got entropy flow due to flows of heat across the system boundary as well. Okay, Gibbs free energy is the other useful quantity that we've got. This is the, roughly speaking, the greatest amount of mechanical work that we can get from a system given its initial state without increasing the volume or allowing any exchange of heat to pass across the boundaries. And as we move towards equilibrium, then we're going to move towards a minimum value for the Gibbs energy. And that's quite useful because we might want to use the minimization of the Gibbs free energy to work out what our equilibrium conditions are. So in a completely reversible process, a decrease in the Gibbs free energy equals the work done by the system to the surroundings minus the work of the pressure forces. And so the sign of the standard free energy change of a reaction will tell you whether the reaction is going to proceed in the forward or the reverse direction. So there's several useful things that come out of being able to quantify the Gibbs free energy. By minimizing it, we can work out the equilibrium state of our system. We can also use it to work out the relationship between a forward rate constant and a reverse rate constant. Okay, so that is done all the time in our chemical mechanisms. Okay, so let's look at how these three things change as we progress through a reaction. So at equilibrium, then we've got the minimum of the Gibbs free energy. We've got an increase in entropy as we go through the system and a decrease in enthalpy. So the equilibrium state of a system is quite a useful thing. We might want to know about the kinetics, which is how we get to equilibrium, but it's always useful to know where we're getting to. And so there are basically various software packages that are able to calculate this equilibrium conditions for you. So Equal is the Chemkin package one. I'm trying to think what the other one. I guess anyone used this part of Chemkin? No, so you're all looking at time-dependent systems mainly. But anyway, they are good and useful to know the equilibrium conditions because we might, for example, want to predict the adiabatic flame temperature that we see under equilibrium conditions, and we might want to know the final composition in our closed system. So how do programs like Equal work to compute these equilibrium concentrations? So you will give them the initial composition of your system, the initial temperature, and then they require thermochemical data. So typically they are reading in these NASA polynomial files. They assume that we've got an ideal gas and an ideal mixture and that the system is adiabatic, and that basically the Gibbs free energy is the sum of the partial Gibbs, molar Gibbs functions multiplied by the number of moles for each species. Okay, so we're going to sum that over the total number of species in our system. So the equilibrium solution to that at a given temperature and pressure is the distribution of n that will minimize that system G. And we've also got constraints that are given by the atomic population. So we can't have an increase in the number of O atoms or an increase in the number of N or H or C atoms. Those things are constrained within our system. So we get a set of equations where we're minimizing the Gibbs function subject to this set of constraints for our atomic populations. Okay, so that will give us the equilibrium concentrations. And also, you know, we're not always just interested in the final equilibrium in a closed system. We are interested in the dynamics of how our system gets there. And that's the kinetics part, right? But I'll come back to this later. Sometimes the partial equilibration is used as part of a mechanism reduction method. So why might the chemical equilibrium calculations be useful? They give us a final product prediction in our closed reactors. We can use them to calculate adiabatic flame temperatures. And actually, in some systems where the chemical timescales are really fast compared to transport timescales, that might be all we need to know. But for most systems, we are looking at the chemical dynamics. So we need to solve the chemical kinetics, which is going to describe the behavior that is away from equilibrium. But the reality is that most systems do at least partially equilibrate. And the rate control constrained equilibrium method, or RCCE, will make use of this partial minimization of Gibbs free energies. Okay, so if those of you that were here this morning will have seen slides of this collapse onto a low-dimensional manifold in our system. So the collapse of system timescales of the fast-reacting species. The sort of partial constrained equilibrium is really representing a very similar process. So this partial equilibrium of fast-reacting species that are then kind of becoming enslaved to the slower species, which are describing the chemical dynamics to final equilibrium. So if that doesn't make any sense now, I will be talking more about that on Friday. I just want to raise it here because there is a connection, I think, between final equilibrium calculations based on Gibbs energy and mechanism reduction methods. Okay, so I'm not sure if that was totally clear really, but what I'm trying to say is the system will start out in a dimension which is the number of species that we've had minus the number of atoms because we've got atomic constraints. And then very rapidly, the dimensionality of our system will shrink as all the fast processes equilibrate or partially equilibrate. And the final dynamics, the progress to the final equilibrium will be determined by the slower processes in the system. Okay, so those will be the non-equilibrated processes. Any questions? I'm not sure if that was clear or not. I'll come back to that on Friday anyway. Okay, and then the final quantity I want to look at is specific heat capacities. So obviously, this is important in our energy equation. This is a quantity that we use in our modelling in various equations as discussed this morning by Professor Matalan. So Cp, which is the heat capacity at constant pressure, is going to be equal to enthalpy change divided by the change in temperature, or if we include that in an integral form, then we've got the initial value plus the integral. Sorry, I'm now moving on to the change of enthalpy. Is the initial value plus the integral of the Cp dt from the initial temperature to the final temperature. So we've got this relationship between the specific heat capacity and the enthalpy. If we use this integral equation, then Cp can be temperature dependent. It's an assumption to say that Cp is independent of temperature because it's not necessarily always true. But if we do say that Cp is independent of temperature, then we can simplify that integral to an algebraic equation where we've just got the difference in temperature multiplied by Cp. Okay, so there's a relationship there. I'm trying to think where we are for time. Okay. So in terms of kinetics, there's not a separation between, I guess, kinetic rate constants and the thermochemical values or thermodynamic values that we've got. The Gibbs energy is really important in terms of determining the reversible rate constants for our systems. And so for many systems, we might experimentally measure the reaction in one direction, but actually the reaction will be reversible. And so it might be useful then to be able to express the reverse reaction rate constant as a function of the forward rate constant. And we can do that through the equilibrium constant So the reverse rate constant will be basically the forward rate constant divided by the equilibrium constant. Okay, so in your mechanisms, if you do go back and have a look at them, more often than not, you'll see the reactions being expressed as reversible reactions. So if you've got a starting mechanism where there hasn't been any mechanism reduction applied to it, then you'll see reactions of this form. And what that's telling you, if there's not a specified reverse reaction, is that Chemkin or whatever package you're using is internally calculating the reverse rate from the equilibrium constant. Sometimes you'll see irreversible reactions, and that might suggest that either the reverse rate has been removed because it's considered to be much slower than the forward rate, for example, or there's specific information about both the forward and reverse rates in the system if both are included. But more often than not, reactions will, in an initial scheme, be reversible. And so we need to calculate this equilibrium constant. And the equilibrium constant can be calculated from basic thermodynamic quantities of enthalpy and entropy using these equations. Okay, so if we know the thermodynamic properties of our species, then we can calculate the reverse rate constants. And so that's been programmed into the Chemkin package. You give it the NASA polynomials, and if you have good data for the NASA polynomials, then you have good data for the enthalpy of reaction and the entropy change in the reaction, and from that you can calculate the equilibrium constant. But what this means is that any errors that we've got in the NASA polynomial fits will lead to errors in our predicted reverse rate constant. So for example, if we have a 5 kilocal per mole error in the Gibbs free energy, then that might give us an equilibrium constant that's off by a factor of 12 at 1,000 degrees. So again, I think this is something that we don't necessarily think about very much. If you do a sensitivity analysis for your system, you're looking mainly probably at the reaction rate coefficient sensitivities, or maybe even just the A-factor sensitivities for your system. You're not really thinking about the relationship between the forward and the reverse rate, which might be actually quite important and depends on the thermodynamic properties, which are expressed through the NASA polynomials. So I don't know, has anyone got any experience of doing uncertainty analysis of thermodynamic rate constants? Oh, good, one person. Oh, 2 people, excellent. But it's not something which is commonly done. But we'll look at some examples of why it might be important later on. Okay, so this is your NASA polynomial file. I don't know if you've never looked at it, look at it. It's giving you basically the coefficients of the polynomials which are used to express CP and the enthalpy and entropy for your species. So in this case, we've got species name, this is CO2. In lots of cases, hopefully it will give you the reference source. That's where the data's come from. And then it's giving you these polynomial coefficients over 2 different temperature ranges. So in this case, let's see. So we've got the mid, we've got from 200 to 1,000 and 1,000 to 6,000. And so there are 2 ranges where the coefficients have been fitted. And if you'd hope that if you plot across the whole temperature range that they at least match in the middle. In actual fact, there's been a few papers by the group from Budapest, from Thomas Strange's group, that show that actually that's not always the case. So they found quite a lot of cases where when you plot the 2 temperature regions, the polynomials actually don't match. And so that can give you numerical problems apart from anything else. I think I've got another example of a NASA polynomial entry a bit later on to talk about uncertainties. But if you're lucky and you've got an annotated file, it might even tell you what the error is in the heat of formation at 298, which will give you some idea about the quality of data. Okay. I think. Are we supposed to break at 1:15? Yeah, okay, so we probably due a break. I'll just see. Yeah, let's just take a break now. Last hour of the day. Sorry, this is the bit where I attempt to explain quantum methods for calculating potential energy surfaces. It's not really a great thing to be starting at this time of the day, but here we go. So I guess the question is, try to explain, I'll show a bit more examples of this later, why it's important to have thermodynamic quantities as accurately as possible in our models. So I suppose the question is, how do we determine them? So we can do it experimentally by measuring the forward and reverse rates for reactions, for example, and backing them out of equilibrium constants. Or we can do it theoretically, which is how quite a lot of data is generated nowadays. And I'm not going to go into too many details here, but I've included it because I'm really just a user of rate constant data, if I'm perfectly honest. We might, we're building mechanisms, or we're using mechanisms and trying to improve our parameterizations within my group. But I don't work on generating parameterizations for data. But I still think it's important to know about where the data's come from that I'm using, or the students and postdocs are using in the models. Because we're trying to develop robust models that represent our systems as well as possible. And sometimes, we might do a sensitivity analysis and find particular reactions where the data is perhaps not as high or accuracy as we would like in it, or it's been estimated, or it's been generated using a low level of theory calculations, etc. And so I kind of want to develop an understanding of where the data is coming from and what that means. So I'm, in terms of thermodynamic quantities, I'm just going to spend the next 50 minutes or whatever just trying to pass over the basics. So if you're working using Gaussian day in, day out, you know more than I do about this particular topic, right? Or at least I hope you do. But basically, in order to calculate our thermodynamic quantities, and also in order to get an accurate potential energy surface to use transition state theory, we actually need to know the energies of our system. So we need to know what that potential energy surface looks like. And if we know that, then we can calculate partition functions for our system, and from that we can, hang on. Oh, I need to turn on the pointer. Where's my cursor? From that, then we can calculate our various thermodynamic quantities. So it's simple, right? All we need to know is the set of possible energies. Unfortunately, this is the hard part, is doing that. And so I'm just going to try and tell you the little I know about this particular topic. So we need to calculate the potential energy surface for our molecule if we're looking at thermodynamic quantities, or for our system, if we've got a reaction through the surface to form products. And we can't measure it, so we need to compute it. And we've got different ways in which we can do that. And ab initio methods, which are the most fundamental, are basically solving the Schrödinger equation, or approximations of a Schrödinger equation. So these are wave function-based methods. They're expensive, and the higher level of detail that you use, the more expensive computationally they become. So, there are people like Steve Klippenstein, Jim Miller, Judith Jardo, all of these people who work in this area who apply these methods fairly routinely now, I would say, for smaller molecules, and give us quite high accuracy information. But unfortunately, when we come to larger molecules, these methods are dependent on the number of electrons in our system, and so they become much more expensive. So it's unusual to see applications of wave function-based methods for large molecules. And later in the week, when I start to talk about alternative fuels, we might be talking about biofuels, for example, or even biofuels blended with fossil fuels, we're looking at some pretty big molecules in our system. And so it's unusual then to find high-level theory calculations for those because it's tricky. So for larger molecules, density functional theory-based methods are more commonly used. So here we're solving for the electron density, and that's much cheaper because instead of being dependent on the number of electrons in the system, it's dependent on the basically just Cartesian coordinates. And so we can move to larger systems without that computational burden. So these are the two main methods that are used in quantum chemistry. The problem with the Schrödinger equation is that it's a PDE in dimensions of 3 times the number of electrons in a system. So you can see that as we, if we move up to larger and larger carbon numbers, then this is going to get pretty hard to solve exactly. So, I mean, even for small systems outside of hydrogen, it's difficult to solve exactly. So we're basically using approximation methods to solve this equation, and basically expanding solution in terms of basis sets and making other approximations. And so the accuracy of the methods that we're using will depend on the level of detail in the basis sets that we're using, and other things like how we're expressing correlation, for example, between electrons. So in terms of an overall summary of approach there, summary of approaches, we've got ab initio calculations, which are basically approximations to solving the Schrödinger equation based on wave function descriptions of our molecules. And we've got density functional theory calculations based on describing the electron density in a molecule. There's been a lot of busy people, right? We've had there's lots of studies of ab initio studies of molecules maybe with 4 to 6 atoms. But as we get larger than that, then we've got a computational cost involved. But that isn't to say that calculations of smaller systems aren't useful for modeling larger molecules. So what I also want to cover, hopefully, before the end today is how we use group additivity to extrapolate information from small molecules to larger molecules. And so having highly accurate information for smaller molecules is still really useful because we can use that to predict what larger molecules will behave like. Okay. Density functional methods are less costly to execute, but they're not really based on fundamental theories. And so they rely on functionals where we don't know the exact form. And so for ab initio methods, what we tend to understand is that as we add detail to the basis sets and we add more and more complexity to our model, then we would converge towards what would be the right solution. But with density functional methods, then we don't have that real convergence, and so there is a bit of an uncertainty involved in using those methods. But again, they have been successfully used for large systems, including things like soot formation, where we've obviously got very large molecules. But it just means that there's probably the need to calibrate's not the right word, to evaluate the methods by comparison with ab initio methods for some systems to get a degree of, to lessen the degree of uncertainty, I suppose. Okay, so I don't know, hands up who's an expert on this topic. I just want to know if any of you are. Oh, good, a few of you. So, if there's any questions, direct them to the top of the room there. So ab initio methods, we're attempting to solve the Schrödinger equation in order to yield information like electron densities, energies, other properties of the system, so we can then extract thermodynamic information, or we can look at using the potential energy surface within other methods like master equation modeling to give us rate constants. So basically, what we're trying to do is to get these methods to converge to an exact solution, but we've got computational limits on the detail that we can use. So we're heading towards basically a full description of the system where we're looking at ideally, all possible excitations of our electrons in the system and all interactions between the electrons. But that's not really possible for larger molecules. And so we're going to be using approximations. And one of the approximations we're going to use is to expand single electron functions as a combination of basis functions. So the first basic approximation that we use is to separate the nuclear and electronic motion in the system. And we can do that because obviously there are large differences in mass. So electrons are going to have high kinetic energy and move very fast compared to the nuclei. So the first thing we do is to solve the electron system, and then we will say that the nuclei are feeling a kind of averaged force from the electron swarms. So we solve the electron motion first, assuming that the nuclei are stationary, and we're basically trying to find the potential energy field that the nuclei are moving in. Okay, so the eigenvalues of the system are going to correspond to the different electronic states, and the potential energy function corresponds to each electronic state of the system. So then when we've got the potential energy surface, we can quantify the motion of the nuclei. So this is basically the Born-Oppenheimer approximation. So the basis of molecular orbit theory is that each electron's motion can be described by a single particle function or an orbital, which doesn't depend explicitly on the motions of the other electrons. So only for hydrogen really are these orbitals exact eigenfunctions of the full Hamiltonian. We're generally missing correlations. But if we start out by considering molecules near their equilibrium geometry, then the Hartree-Fock theory is a good starting point for more elaborate methods that we'll use to get better approximations of the Schrödinger equation. So this is the most basic level of theory, to start with a Hartree-Fock calculation and then use higher order methods. But even this basic theory scales as n to the power 4, where n is the number of electrons. So even so, as we move towards larger systems or larger molecules, the computational cost is going to increase. Okay, so this is basically our Schrödinger equation, and includes partial derivatives with respect to the electron positions. We can't solve it exactly, and so we're going to expand it as a function of basis, various different basis sets. And basically what we're doing in that way is collapsing what is a partial differential equation system to a generalized eigenvalue problem. So I think it's analogous, I suppose, to using finite element methods in CFD type models, where we're basically expanding as a function of the finite elements and collapsing everything onto an algebraic system. And then what we want to know is the lowest eigenvalue of the system, and that's giving us the physically important one that corresponds to the potential energy surface. So in terms of basis sets, we're basically trying to turn this set of PDEs into a set of coupled algebraic equations, and we can do that with basis sets of different types. So the most fundamental are Slater-type orbitals, which are basically solutions of the Schrödinger equation for hydrogen-like atoms, but quite expensive to calculate. So we would tend to use Gaussian functions or sums of Gaussian functions to try and reproduce the basic shape of a Slater-type orbital, which are physically less realistic fundamentally, but are quicker to compute. So I don't know, but I guess that's where the program name Gaussian comes from, that basically most of the basis functions are based on Gaussian-type basis sets. So the higher the number of basis functions that we have in a basis set, then the more flexibly we can describe the system in terms of electron positions. And that means that we can more easily describe complex behavior like non-harmonic oscillations, for example, polarization, blah, blah, blah. But the more detail we include in the basis functions, then the higher the computational cost is going to be. So what we want to do, ideally, is to include a complete description of all the correlation energies within the limits of the Born-Oppenheimer approximation on our basis set. So ideally, we want to include all the excitations that are possible in our molecule. It's not always computationally possible to do this. So you might sometimes see truncated versions of these interactions. So if we, for example, you might see a method which is CISD. That's only going to include single and double excitations. And so if you've got triple excitations in your system, then this is going to be an approximation. So ideally, we would want to head towards a system where we can include all of these excitations and the full configuration interaction, but computationally, that's going to be prohibitive for anything but small molecules, really. So, yeah, depending on the size of our system, will have an impact on the method that we can choose. What did I want to say here? So, yeah, you might see different translations or approximations that are giving constraints on our system, and we might basically want to force a physically correct behavior, for example, within the electron correlation, and methods like F12 are, you might see are ways of doing this. So in this particular formulation, then we're forcing the physically correct behavior when electrons are close to each other. In other approaches, like the couple cluster approach, we take a transformation of the system, which makes basically makes the system easier to solve in terms of representing interactions. So instead of explicitly constructing linear combinations of basis functions, we do a similarity transformation of the system, which gives us a different set of equations, and now our adjustable coefficients are inside the exponentials, and we get a large system of algebraic equations. So this means that single, double excitations, etc., are included explicitly in the model. It's more expensive to solve. The advantage of this method is that basically it basically guarantees us kind of extension of the model. So if we double the system, then we double the energy as we're supposed to. So it gives a physical constraint on what we're doing. Okay, so when we're looking at different methods for computing our potential energy surface, then if we're looking at very high accuracy methods, then we might see something like couple cluster, single, double excitation. In this particular case, and the triples are included in brackets because they are modeled using a slightly cheaper perturbation type method. Okay, the downside of this is that basically our CPU now scales as n to the power 7. So obviously for systems with a large number of electrons, that's going to be prohibitive. But I'm trying to think what the limitations now of this method are in terms of system size. Maybe 4 or 5 atoms it's possible to do using these couple cluster type methods. So perturbation methods are also used, and so here the missing electron correlation in the wave function is added as a series of perturbations to the wave function to different orders. So you might see terms like MP2, 3, 4, that's giving you second, third order perturbations. So if you see a method CCSD, triple in brackets as I showed on the last slide, then this is basically calculating using couple cluster methods for single and double excitations, but including triplet excitations using perturbation methods. CASB2 is a multi-reference electron correlation where we might not just start with a single reference function, Hartree-Fock function to build the form, but we're using multiple ones, and that again gives us more flexibility at increased computational cost. So we've got software packages that have been developed over the years to do all of this. As you can probably tell, I don't do this, but I think if you are using these methods like Gaussian or MolPro or any of the other packages, then the key is to kind of have an understanding of the level of accuracy that you are using, rather than treating them like a black box. So I'll show some examples later of differences between different levels of accuracy, but it can really strongly affect the calculation of rate constants by orders of magnitude, the difference between using a low-level calculation and a high-level calculation. So I think I inherited this slide actually from Bill Green, and his comment, I guess his group's used to applying these methods. His comment was that actually if you put the same inputs into these software packages, then you should get, and you use the same basis sets and you use the same approximation methods, and you should get the same answers out. And so they are equivalent in that way. So it's more about really understanding you know, what methods you're using, but they should be equivalent. So if we've got the quantum chemistry package and we can compute the potential energy surface, then how do we compute the energy levels that we need to calculate either thermochemical data or energy-specific rate constants that we might want to input into a master equation code to calculate rate constants at different temperatures and pressures. So in this sense, we need to also include the internal energies of our system. So molecules, you know, they're not stationary, they're semi-rigid structures which might be oscillating, flying around in space, vibrating, rotating, and so we need to also understand the internal energy corresponding to a different quantum state. And the observable properties are averages over ensembles in thermal equilibrium. So first of all, then we need to solve the Schrödinger equation for the nuclear motion, and then determined by the shape of the PS near the equilibrium molecular structure. So in terms of vibrations, the simplest approximation there is to use a harmonic oscillator approximation, and that's not necessarily always going to be the highest level of accuracy. But here, we usually start out with a harmonic oscillator approximation and then make further corrections if we need to. But basically, this here, we're assuming then that the vibrations are of small amplitude, so we've got no floppy degrees of freedom, and it's a good approximation then to use a harmonic oscillator to calculate the vibrational frequencies in our molecule. So if this is the case, then we can use the lowest order terms in our Taylor expansion of the potential energy surface about the equilibrium. And so we get quadratic terms, removing the sort of cross terms, leaving a set of harmonic oscillators. And there are cases, though, where this is not valid. So, for example, where we've got internal torsions in our molecule, or we've got hindered rotations in our molecule, these can have an impact by actually lowering the overall energy barrier and therefore making the reaction to proceed more likely, for example. So for a particular system, it's important to, I guess, recognize whether you need to include further approximations like hindered rotor or whether or not simple harmonic oscillators will be sufficient. Okay, so one example of hindered internal rotation is given here for ethane. So you can see here that the energy is changing with the dihedral angle. Okay, so this is not a simple harmonic oscillator, and actually that can have an impact of lowering the barrier for a reaction, for example. I don't know, I was going to show a movie, but I think that might be too complicated at this stage. Okay, so our partition function characterizes our statistical properties of the system at thermochemical equilibrium. And it's the partition function, I think I might have said this earlier, is defined as the sum of all the available quantum states. G is a degeneracy factor here, or the number of quantum states that have the same energy level. We're usually approximating each of the vibrations as a harmonic oscillator, except when it's not okay to do so, I suppose. And so the quantized energy of a harmonic oscillator with a given frequency is expressed here. And then we can calculate the partition function for vibration. Where do we get the vibrational frequencies from? We can do it experimentally. I guess maybe if you're doing Ron Hansen's lectures, then you might have looked at that this morning, I'm not sure. Or we can do it using theoretical calculations. So we can use couple cluster methods, for example, if we've got small molecules, or we might want to do a density functional theory calculation if we've got a larger molecules. And this DFT type application is not particularly computationally expensive. So just a quick aside on the DFT methods. So here we're not solving for the wave function, we're just using a description of the electron density functional. And we need to find the correct electron density where we can get the electron energy at a selective molecular geometry. So the general mathematical form of the energy functional is not known. So this is the reason why it's hard to get a kind of converged system using these methods. But basically, what we do here is to proceed by varying orbitals, one for each electron, as a function of physical space. So it's much easier to expand these functions in 3 variables than it was to expand the Schrödinger equation, which is going to be a function of the number of electrons that we've got. Okay, so these are convenient and fairly accurate ways to compute the potential energy surface for low CPUs. We can maybe get to a kilocalorie per mole accuracy. That could lead to errors in rate constants of maybe a factor of 10 even, but sometimes actually if we've got a whole new modeling system, that might be pretty good to get a rate constant within an order of magnitude. Okay, so generally then functionals are tested or evaluated by comparing against ab initio calculations or wave function-based methods, which are considered to be at least close to exact. So programs like Gaussian, MolPro, etc., can compute the energy density as a function of the potential energy surface, and from that we can get the derivatives with respect to R. Higher order derivatives will give us things like the frequencies of our vibrations. So one of the issues here is that we are looking to optimize the system and find the local minima, but what you really want is the global minima. You don't want to get stuck in a local minima, and so you have to provide a fairly decent guess. And that's actually also analogous to sort of CFD methods where or optimization methods where you're trying to optimize a function. Okay, so then we can compute the Taylor expansion of the potential energy surface, and then the second order derivatives will allow us to calculate the frequencies for our vibration modes. And this is done automatically for you in Gaussian, and we'll see that so eventually we're trying to compute potential energy surface and the activation energies or the barrier heights that we want to use to describe our system, and also the vibrational frequencies which will feed into methods for calculating rate constants. So a quick comparison of the two methods then. So ab initio methods are, the objective here is to find the wave function, whereas DFT methods we're trying to find the electron density function. For ab initio methods, we should, by increasing the complexity of our basis sets and electron correlations, we should be able to find a systematic way of improving the accuracy of our method. So by adding more complexity and more detail, we should converge upon a more accurate solution, whereas the same is not necessarily true for DFT methods. So for DFT methods, I think evaluation using ab initio methods is quite an important part of that approach. The downside is that for ab initio methods, for anything but smaller systems, the computational expense is quite large. So they're mainly restricted maybe to small molecules, maybe C3. I don't know, you might know of systems where they've been used to look at larger molecules. The cost of DFT methods is quite small, and so they can be used to look at hundreds of atoms, which is useful if we're trying to model soot formation or other large molecules like that. I would say that probably all of these methods can be used with little expertise because you can just run Gaussian, right? I wouldn't trust myself to do it, but so I think the issue is that you know, knowing what the level of detail that you're using and having some idea of what the level of potential uncertainty in your outputs is actually quite important. And basically, as a user, I would quite like to know that for the information that I'm putting into my model. So I quite want to know, you know, if theoretical methods have been used to calculate heat formation, I quite want to know what the potential uncertainty of that is, because that will feed into my calculation of equilibrium constants, etc. And for rate constants, the same. So yeah, I don't know. I mean, I think I'll talk about this a bit later on, but there are now emerging studies that are attempting to express the reliability of these methods. I think it's more difficult to do for density functional theory methods than it is for ab initio ones. So, you know, both of the methods are useful, I think. Okay, so at the end of the day then, we need to combine all of this information into our partition function. So we've got internal motions like vibrations, rotations in our system, and also translations. And then we can calculate the total partition function of our system and use that to either derive our thermodynamic data or to give us the full potential energy surface and microcanonical rate constants to feed into our master equation work. I think I'll skip that slide, to be honest. So one of the things I mentioned was electron correlation, and single molecular orbital methods are going to ignore direct correlations in between electrons. So I've tried to express this in a diagram here. One method is basically to say, well, look, our electron is subject to a field from a cloud of electrons, and the other is looking at the interactions between individual electrons. Methods like complete active space methods are trying to give you a high level of this electron correlation. And coupled cluster methods also construct multi-electron wave functions to try and account for electron correlation. And that's going to add to the computational cost of the method. Okay, and then we've got other potential pitfalls to look out for. So the harmonic oscillator approach doesn't necessarily always work. We might have hindered rotations. For ring-type molecules, we might have effects like puckering of rings. rotations around carbon-carbon bonds, etc. And so sometimes we have to go to higher levels of approximation to include these types of behavior for our molecules. So I don't know, I'm only a user of the outputs of this type of method, but I'm always interested in knowing what the uncertainties are in the information that you receive. So people like Steve Klippenstein have a very, very good feel for a system and a particular level of theory of what the uncertainty in barrier heights might be, or the uncertainty of frequencies might be. So those are the people to go to, I guess, for this type of information. But basically, I think if you're not really using these methods in earnest, this diagram is probably what you need to know. So this is looking at basically the level of theory and how it affects the accuracy of electronic structure calculations. And there's two, it's a matrix basically, I suppose. Is that the right word? It's a surface. So you've got a level of accuracy that depends on the basis set and the complexity of the basis set. So right at the bottom end here, we've just got Slater-type orbitals. As we increase the number of different excitations that can be represented, then the accuracy goes up. Then we finally move to coupled cluster. The accuracy goes up again, and then we get to a complete basis set, which is, I guess, the theoretical maximum that we're trying to achieve. And then we've got different levels of electron correlation. So the Hartree-Fock is not really including electron correlation. We've got perturbation methods then for doing that. Then we're moving up to complete active space calculations, then to coupled cluster, and then eventually to full correlation interaction. So as we move down the center here, so increasing the complexity of our basis set and increasing the description of our correlations, then we're going to increase the accuracy of our system. But that's going to come at quite a large increase in computational cost. Okay, so I guess the picture on the right is really just saying the same thing. Do I want to say anything about this? I think I'll move on. Okay, so that's, I think I'm just repeating now what in words what I said on the last slide. So the complete basis set is a kind of extrapolated estimate, really, of that you would expect if you're using an infinitely large basis set. So this is something where I think we probably don't get there, but we have maybe if we extrapolate, we can get an idea of what that might look like. And then as we increase our representation of electron correlation, then this is increasing the level of detail that we're using in terms of how much a movement of one electron is influenced by the presence of the other electrons. Okay, so here we're trying to get to full configuration interaction, but again, only possible for small molecules. So I think more common probably now is to use what we call composite methods. And here we're trying to combine maybe methods with a high level of theory, but small basis sets, with methods that employ lower levels of theory in terms of electron correlations and larger basis sets, and try to combine the information from the two. So one way of doing this, for example, might be that you use two different levels of theory for your system, and you work out what the error is between the two, and you try to extrapolate that to a higher level of theory. And then you might do the same with including additional information on correlations. And so there are quite a lot of these composite methods around. The least expensive is CBS-QB3. I don't know if that means anything to anyone. So this is a method that I commonly see in terms of being used to calculate data for large molecules that we might use in a biofuel system, for example. But actually, for applications where I'm looking at this particular study by John Summers and Kieran Summers and John Simi, where they actually benchmarked all of these different methods at different levels of accuracy against the most accurate data that you would expect, which would come from active thermochemical tables. I'll say more about those a bit later on. But if you look at CBS-QB3, which is the method that I most commonly see in papers, then you can see that actually the distribution is here for lots of different systems for oxygenated hydrocarbons. Then the estimated heat of formation using this lower level method has quite a wide distribution. So the units here are kilojoules per mole, but the maximum error is around plus or minus 15 kilojoules per mole using that low level method. And that would give you pretty large errors in the calculation of reverse rate constants, for example, or heat release in your model, and also would feed into errors in rate constant calculations. If we move up the order of accuracy, then you can see that these distributions are tightening. Okay, so the tighter the distribution, then the lower the level of uncertainty. And so G3 and G4 composite methods, which are the pink and the blue lines, have much tighter distributions. But actually G4 also has a bias, and so it tends to underpredict heats of formation, for example. Whereas G3, at least the peak is on 0, even if it's a slightly wider distribution. Okay, so as you increase the level of theory, then the uncertainties do shrink. And I don't know if this is the right way to go, but the suggestion in this paper was that if you have random errors, so you don't have bias, then the best thing to do is to apply various methods and to average them to get your suggested heat of formation. And that's what they've done for data for certain biofuel, oxygenated biofuel molecules. If you do have a bias prediction, then I'll mention in a minute, there has been some work done by Franklin Goldsmith on correcting these according to the types of bond structure that you've got in your molecule using bond additivity correction methods. Okay, so this data is important in your mechanism, and if anyone did do uncertainty analysis based on thermodynamic data, you would find, particularly, for example, for low temperature chemistry routes, chemical pathways, that actually uncertainties as large as 10, 15 kilojoules per mole can be really significant in predicting things like ignition at low temperatures. Was it too late to start asking questions? It probably is, isn't it? Let's just go to question 3. So what do we think might be the biggest way in which an error in the thermodynamic data could affect predictions in our model? Has anyone looked at uncertainties? I think 1 or 2 people said they had. Has anyone got experience of actually, modifying heats of formation and seeing what impact that has on your model predictions? Nobody? A bit? You want to give us an example or no?
I'm working on an automatically generated find the most sensitive thermal parameters and calculating them stable model match the data more closely.
Yeah. Okay. Right. Can you remember what species are particularly important?
It was like the first reactions with
So,
the first reaction.
Okay. Interestingly, I'll come on to this a bit later on, but interestingly, we also did a thermodynamic sensitivity analysis of N-heptane, and it's peroxy radicals and things like QOH molecules from the low temperature chemistry can be quite important. So that's one impact, yeah, that is going to affect, in that particular reaction system, you know, maybe the isomerization of RO2 to QOH or backwards, so that we don't have information specifically about that reverse reaction rate. We're calculating that from the equilibrium constant. And whether we get ignition will really depend on that reverse reaction is one example. So calculation of reverse rates is key. I'll actually put that here, actually. So isomerization of RO2 to QOH, I think that's true in the N-heptane system. Prediction of heat release rates for our model, and adiabatic flame temperatures. You know, we have high-level theory calculations for small systems, but we are, in terms of alternative fuels, we're moving towards trying to predict larger molecules, and we're also trying to predict now for biofuels. So these are molecules which contain oxygen, single oxygen bonds, double oxygen bonds, and that changes the game a little bit because most of the theory has mostly been applied to small molecules or to alkanes, right? I think it was Franklin Goldsmith actually looked at 200 molecular species of interest in combustion chemistry, including double bonds, triple bonds, oxygen bonds, double bonds to oxygen, etc. And tried to get a systematic feel for bias from our theory calculations. And what he did was developed what's called a bond additivity correction method, where specific corrections for different bond types were given. And using those correction methods, even using composite methods or lower levels of theory, using correction methods could get uncertainties of approaching half a kilocalorie per mole. Okay, so that's a reasonably useful level of accuracy. I think Steve Klippenstein would claim that using very high levels of theory, they can get within 0.2 kcal per mole, but a large CPU cost and for small molecules, not large molecules. Okay, so half a kcal per mole, I would consider that data worth having for sure. I know we're running out of time, but okay, we've got 8 minutes left. I want to say more about active tables a bit later on, but what active tables do is try to gather together all the information that we've got on a particular system that might apply to a certain species. So it could be experimental data, it could be high-level theory data, and constructs a thermochemical network between the species, and then tries to optimize that network so that it's choosing thermodynamic parameters that give us a minimum level of error with the data that we've got. So I'll show you an example of a network later in the week. But basically this, I guess, is the holy grail of thermodynamic data. So if you haven't looked at the active thermochemical tables, then I would do that. I think when the Burkat NASA polynomial tables were being updated regularly, that actually data from the active tables was being regularly fed into there. And so you should be able to see in the Burkat table what the source of data is. If it says, what's the acronym, ATCT, then that usually implies a very high level of accuracy because it's been optimized within the thermochemical network. Otherwise, you might see something like Therm. Anyone use Therm? No. So Therm is using group additivity methods to estimate thermochemical quantities. So I've given an example here for heats of formation at 298. This is for alkanes and for different numbers of carbons. And so what it shows actually is that for, at least for alkanes, if we look at heats of formation and specific heats, that these are fairly linear in terms of the number of carbons. So what this suggests is that actually, if we have really accurate high-level theory data or really good experimental data for systems with 1, 2, maybe up to 4 carbons, then that is enough to determine a trend that we can then fit, and we can then derive incremental values as we go to higher and higher numbers of carbons. So this is called the group additivity method. So what we're doing here is we're saying, okay, we've got this linear fit, and so we can assign a value to the increments which are caused by just inserting 1 more carbon and its 2 hydrogens into the alkane chain. And that means that we can now estimate those thermodynamic properties for any carbon chain length. So that's great if you just want to look at alkanes. But we don't really, because we're trying to look at alternative fuels, because we're trying to move away from burning fossil fuels, right? So, so there needs to be, some updates to information to use group additivity for other types of molecules. But it's a system that certainly works pretty well for straight chain molecules like alkanes. Okay, so you'll find programs like Therm or RMG. I don't know if anyone's got any experience of using RMG here. Yeah. Basically, they are using group additivity type methods to estimate thermodynamic data for large molecules where there is no high accuracy reference data. So they're using, though, training data for small molecules where possible to then give you those increment values that you can then use to predict the data for larger molecules. I mean, if I've got time, I'm hopefully just going to show you a case study of us using RMG for some oxygenated fuels, hopefully later in the week. So this method goes back to Benson's book, which I hope I've listed in the references. It's not new, but basically the method is improving because the reference data that we have for small molecules is improving all the time, and that gives us better group estimates that we can then use to predict for larger molecules. I'll be rushing now a little bit, but so the basic concepts are that we've got different groups within a molecule. So we might have carbon-carbon attached to 3 hydrogens, or carbon-carbon attached to 2 hydrogens if it's in the straight chain. And in oxygenated molecules we might have a carbon double bond to an oxygen or carbon single bond to an oxygen. And we want to be able to estimate what the change in thermodynamic properties is by adding each increment of the group in our molecule. So this works fairly well until we've got things like symmetries in our molecule. So for standard entropy, then we do need to take into account symmetry effects and optical isomerism. But in general, we can basically express our thermodynamic properties, so that might be entropy, enthalpy, specific heat, as a sum of the groups in the molecule. So just by summing together the incremental value for each of the groups. Radicals we might treat somewhat differently. I think it was Joe Botzelli actually that developed, or his group that developed this method. So if we've got a hydrocarbon radical that we might get, for example, by pulling a hydrogen off N-heptane or some other type of alkane, then we use a slightly different approach where we actually use the heat formation of the parent fuel as a starting point. And then we have another value for the bond dissociation group, and then we've got the heat formation of the abstracted hydrogen atom. So this is a slightly different method for radicals, and I think this is probably used in RMG fairly commonly as well. Okay, so I will talk about automatic mechanism generation, but these types of codes, they are using group additivity to estimate their thermodynamic properties. But for the most part, it probably works. We've got some challenges for things like ring compounds. where we got ring strain in the compound, and that's not accounted for in the group values because they've been derived using training data from alkanes, which are straight chains. So for highly branched compounds, we might also not get such great estimations. And one of the things that we found is that there is, in the basic form of RMG, there's not quite enough data for carbon-oxygen bonds or carbon double bonds to oxygen that we might have needed for our biofuel molecules. So again, I would say that RMG is definitely not a black box, and you need to be aware of the training data that's in there for the groups in the molecules that you have that are of interest. So I think basically most of these methods have been developed for straight chain alkanes, but we want to use them for far more complex molecules than that now. For predicting potentially the combustion of low carbon fuels. Oh, I think we've nearly made it to the end. I can see everyone's looking pretty weary now. So thermodynamic data is pretty useful because it gives us our final equilibrium. Even if we want to study kinetics, it's still useful to know where we're going. So we can use programs like Equil to compute equilibrium compositions or adiabatic flame temperatures, but they do rely on accurate thermochemical parameters. So they're reading information in the form of NASA polynomials usually, and those NASA polynomials might come from active thermochemical tables, which are using high levels of theory and that network optimization, or they might come from applications of therm, which are using group additivity. And so there's a really big difference in the level of accuracy from those different methods. Group additivity is very fast to apply, and high-level quantum chemistry is difficult to do well. Both are useful, and we wouldn't be looking at any larger molecules if we didn't have group additivity methods. So whatever the system or whatever the method, we will have uncertainties in our thermodynamic information, and that will feed through our model into uncertainties in our predictions, which I will talk about more on Friday. I think that's the end of today. Sort of wish I hadn't strayed into quantum chemistry because I don't like it. I find it difficult to explain. But anyway, hopefully at least you've got an overview of the importance of looking into the level of accuracy in the models that you're using. Any questions or I think a half of lager would be good. Don't film that. Any questions? Thank you.